Hey, did you hear me? God, what an inspiring introduction. So I just wanted to share with Riju the sense of like honor of being here and excitement. And I remember for a long time before Eterna, I worked on computer graphics, and I went to this conference called SIGGRAPH. Any of you been to SIGGRAPH? Okay. Oh, sweet. Yeah, that's very fun. Anyway, it's this really, it's big, okay? And there's signs when you get to LA, welcome to SIGGRAPH 2015, and it's filling up this whole convention center and stuff. And every now and then you run into this old timer, and he says, oh, I remember in SIGGRAPH 72, it was in the back of a Hilton hotel. There was 10 of us. We were talking about rasterizing triangles, and I feel like that's who we are today. Riju and I were joking about growing old with Eterna, but I think that we're going to be those people who are going to tell all the young kids we were at EteRNAcon 1, and they're just going to be totally amazed. Yeah, and it's not even in the back of a Hilton; it's in Stanford, so we're already doing better. Okay, so. It's one of the really fun things for me about working on Eterna and this whole community is that I'm not really a biochemist at all, but I do care about computer algorithms, and I care about labor and what is the role that humans are going to play in the context of computers that are getting smarter and smarter and that understand more and more of the world around us in the same way that we do. And of course, this is a sort of question at the heart of Eterna also. Why are we all doing this? Why isn't it just that computers are doing this? And I would say, clearly, there's something really important here, because we've shown, for example, in the PNAS paper that resoundingly, the Eterna community was able to beat the best computer algorithms. So that's a really amazing thing. What's going on there? How could we explain that and rationalize that and explain it to others? And I've also become interested recently, basically in business, and I mean that in the best way, which is not trying to ruin the world or steal all those resources, but rather to create things which are self-sustaining, which are net energy positive. And Eterna is this amazing, beautiful thing, but it was also created inside of the university and was allowed to sort of be protected from the outside world by these hallowed halls. So I've thought a lot for the past couple of years about, here we are in Silicon Valley. How would we go to a venture capitalist, for example? Okay, these guys, they're all spreadsheets and numbers. They don't give a crap about the community. They don't care about the color scheme or the badges or anything. They're about, is this going to be net energy positive? Is this going to make more money than it's going to lose? How can we go to one of them and justify what it is that we're doing? How can we convince them that over the next 10 years and 20 years, a community like this, working on activity like this, is actually going to produce more for society than all of this effort that's going into it, all of the money and cost. And that is going to be unsustainable forever. And so I just wanted to maybe forget Eterna for a second. Eterna is fine, and it is sustained, and it is on good, firm footing. So this is not a question about Eterna. This is more a question about how would you go and justify a project like Eterna to a venture capitalist. And one thing that you might say is, well, humans are better than computers at solving these important problems. So that seems like a really important thing, right? We want to solve these problems. We have a new way of solving them. They're better. But I can imagine someone saying, well, maybe they're a little bit better, but computers are a whole lot faster, and there's a whole lot more of them. Maybe we'll be willing to solve the problem slightly less well, but a billion times faster. How does it scale to have humans solving problems? Right? And I would say, no, well, actually, it's more like the strategy market. The humans are going to teach the computers, and that's going to be the whole goal. And then I might respond, well, that sounds like a good idea, but that's a losing game. Soon the computers are going to know everything, and what are the humans going to be left to do? And then I might say, well, they're just wonderful people, and I want to hang out with them. And they might say, well, that's great, but that doesn't make us any money. Okay, so that's really the challenge, and I have some thoughts about this, but I guess I'm allocated until 10:45. So what I thought it would be fun to do is I want to share with you guys some of my thoughts, but I also thought it might be fun to let you guys think about and answer this question. So what I'd like to suggest is that I'm going to allocate you guys into groups of 4, pretty much geographically, as you look in front of my eyes, and I want you guys to spend 5 minutes to come up with a couple sentences as to how we could justify the existence of a community-based science platform as a sort of economically feasible model for the future of science and research. Okay? So I'll write that question. Oh, there's not really a board here. I'll write it on the board. But in the meantime, I'm going to put you guys in groups. Ready? So we do this with a super group. U4. U4. Can I ask you to join the group over there? Sorry, this is the college professor. I have to do this. You guys, U4 right there, or U5. 1, 2, 3, 4 in the back. 1, 2, 3, 4 right here. 1, 2, 3, 4. 1, 2, 3, 4. And I'll write the question on the board, and then I'll see you guys in 5 minutes.
And so,
Yeah.
Do you tell the Hangout of this live stream that you're doing?
Oh, okay.
It's in that.
So I'm gonna tell the Hangout that we're gonna spend 5 minutes talking about this, and then we're gonna come back and look at the answers. Is there a way to get access to this screen?
Yeah.
Colleges are going to eat it up.
So, why it says
Okay, so I put the question up on the board there.
I can check with you. Yeah, that'll be okay.
But how much of that work prepared are you if you supercomputer, you can get a computer to tell them what happened. I mean, like for millions and millions of CPU hours, like that work that like with one person easily, right? So harvest human intuition, and you don't have to pay them. Yeah.
That I did not give it insight.
I think that's I mean, yeah, you can put that as against the learning. Consolidate. Yeah. Like that.
Because people
Sorry, can I crash your anything for a second? Do you have the slide, like, well, obviously, do what needs first, but do you have a slide, like, summarizing eternal, like, the good solution that EteRNAcon had for its okay, but you showed that at one point, that it had the best solution. Can you just show me the solution? Sorry, or something. Sorry. This way. Remember. Yeah. Yeah, that one, and then, but there was one where EteRNAcon had the highest one. Yeah. Can you, oh, wait, you're talking about that? Your slide shows way too small. Yeah, okay, good. Can I get those two slides? Do you mind? Okay, thank you. Thanks. Yeah, this one. Right, this talks actually. And I that's how I did
educated in different
I'm probably not now.
So opening up.
No. I was like, God.
Outside ideas. That's it. Anyway, okay. So
Yeah,
that's
oh, good.
Yeah, so I can kind of summarize like, in terms of ingenuity of people and like way more cost effective. Like maybe your supercomputer. Yeah, but it's not just
I think that the cost is already.
no.
when I started,
Added value.
all the very yeah, I know it won't go that far, but I just think
Especially if it's like
kind of where we are now. We started on a problem.
I think that-
Solve this.
I think that
yeah, I think that's what we were talking about. I just feel that it's pretty cheap for your to run the.
Okay, one more minute.
Control.
I mean, it's kind of like the venture capital. All you have to do is find just push net. Yeah.
So I think it's really.
Especially once we start.
I thought you meant like
Almost like half. That's what I feel.
All right, all right. All right, you guys, the bad kids in the back. I'm really looking forward to hearing what you guys are saying, and I've already heard some actually really brilliant stuff in the audience. And I will, let's see, I don't want to go first or last because that seems a little weird. So I'll go right in the middle, and let's start in this. Did you guys go, or you guys weren't really a group?
So we crowdsourced it, so we started on a chat.
Oh, cool. Wait a minute. Wait a minute. Yeah.
No, that was actually our point. We think outside the box.
Wow, I love it. Okay, go for
Just
it.
got one answer then. W.H. Bob says there's one, large amount of free man hours, two, many eyes on a broad subject, and three, we would say actually like adding to that, it's kind of like it's crowdsourcing. Like if you done properly, crowdsourcing can be like a leveling playing field, and people that don't have access to like premium high level institutions can get access to them if crowdsourcing is done correctly. So it's less about serving who's sourcing rather than serving those who are being sourced.
Cool. Let's see. There's a group right here, right?
A couple of things that we primarily talked about was, first off, is that there's not just that there's a lot of eyes on the same problem, but a lot of different people who all have different experiences and can bring different things to the table.
Okay.
That might have been a.
I think you talk about you mentioned that a lot of this information is publicly accessible. Maybe they're not in like a library or database, but that's probably something that can be done. But I think the important thing is it's public, right? And it can be shared, and that's very powerful, right? Because that's where you start getting kind of like what Ben mentioned, right? A problem and that'll drive creativity, right? Because different people look at
Cool. Very, very cool. Okay. How about going to the back group?
Hello, EteRNAcon. Do you think that regardless of any doubts that you have in getting funding, proving the bottom line, to try anyway instead of needing to start meeting people because you don't know you might fall apart? So try is the first. The second suggestion, I think everyone's engaged about focusing our research on specific diseases, so like Johan's work in terms of like heart disease. Those are the things that anyone can understand. Whereas trying to explain the fundamental physics of how our navel gets into a really long conversation with these eyes will glaze over. So focusing just on tangible things that they can comprehend, like if we can legitimately say we're working towards a cure for cancer, that's something that you can say in a few words and later. Our third idea, we phrase it as sell hot dogs, and I'll explain what that means because we don't have it completely thought out since we're in but basically, if we can't find a way to monetize our core researcher platform, consider running some kind of parallel project that does monetize. So for example, if you want to sell ice cream and no one's buying the ice cream, but they want to buy hot dogs, then you can give away the ice cream for free and sell hot dogs. But we don't have a particular solution as to what the hot dogs are.
I think the hot dog is called the National Institute of Health.
Yeah, well, actually, a fifth idea looks just kind of obvious, is finding other fundraising opportunities. But our fourth idea, I kind of did it at the last second, you said you wanted four. So I would appeal to their ego because they're extremely egotistical. And I would also appeal to their sense of wanting to leave a legacy because a lot of these people do think long term, beyond their own lifespan, have a sense of pride. So I would appeal to that. And in the course of trying anyway, just remind them of the blessed reach and what they can do to make a difference because even though they might seem heartless, who knows, maybe they'd like to be reminded of their humanity.
Oh, very powerful stuff. And just a side note, this is not, we're not really hard up for cash. So don't worry. It's not about funding EteRNA as much as it is about having really powerful arguments for why we should be doing this, perhaps even on an economic level. And these are all extremely powerful arguments. Okay, so the group in the middle there.
Yep.
Hi. So one of the things that we talked about, we didn't really come up with like 4 sentences, but we just came up with just some thoughts. That you need people constantly in the process to constantly do a back and forth, kind of improving and just observing kind of a customer service kind of things and what one. And one thought that that we had just kind of at the end was that you know that
we also talked about businesses having as their own metaphor automating more things, and therefore there was a market for folks understanding how to do a cooperative enterprise or task that is done partially by automation and partially by humans who are evaluating the results of what the computer is proposing and then deciding whether the computer needs to be told more things because it's getting an unrealistic idea or whether or not to accept what's coming. So we think there's a larger kind of business-oriented play beyond biology, but into the business world itself about decision-making.
Cool. Man, I'd give you guys money. Can we go into that corner over there?
Okay. Yeah. So
We discussed, well, first I was personally curious about the way the question was framed, because it seems, at least my perception of venture capitalists, is they're just as you described, Adrian, in the beginning, they want to see the numbers with revenue, with the growth, all this stuff that fits into a particular template. So maybe the obvious thing to do is build one useful, economically valuable thing, get those numbers in place, and then show that to them. So go to meet their template rather than trying to get them to sort of see the world our way. And then I really liked a lot of the answers that people have already given. So I think we could just reiterate or amplify on comments, especially the last one. I think abstracting the process and then making that into kind of a service that could be applied to other areas, maybe not necessarily science or the pursuit of understanding RNA folding, but other challenges that other companies have also done similar, like the Netflix challenge. They put a prize, $1 million up to improve their algorithm. So there are other models that already exist that maybe we could just copy those as well. Did you guys know? Yeah, okay.
All right, so ours wasn't really completely for economical standards or whatever, what we're looking for economically, but just kind of prove how you can say the difference between Miami people and not computers right now. And I said, I mean, our goal, I would think, would be it's to get to the point where we can use computers by themselves. And we're not at that point yet, not even close. And I mean, the fact that we have 3 different algorithms right now that's on EteRNA is proof of that. We got NewPack and we've got Beta 2 and Beta 1.85. So if we got 3 algorithms that all of them are perfect, and we still have that. Plus, we have EteRNA 3D coming out, or so we said it's coming out. Is that so? We're going to a completely new interface. So once we do that, then we've got computers doing the stuff that we were doing, the 2D version, and now we need more humans to figure out how to program computers to do the 3D part. So we still have a long way ahead of us with just humans and not computers. But I would think that that would be our ultimate goal, not to figure out how can we get just humans to do it and not computers, but how we can get computers to do it and not just humans.
Mm-hmm. Cool, lots of good thoughts here. I'm trying to capture this. So we've got a little bit more time until the computers take over, and our goal is to usher in their ascendancy.
So,
Did we miss a group in the corner, or were you guys represented? Okay, good.
So we tried to look at the point of view, why is it that we see citizen science as economically sustainable? And there were kind of 4 points that came up. One is creativity. And citizen science can be creative in ways that others can't, because they're a large, diverse group that will think outside the box. They haven't been constrained by, being engineered down a particular path in their courses. This is how it works. They don't know how it works. They'll figure it out in ways that other people might not even look at. Second is science is hypothesis driven. And as computers and algorithms improve, what we need the people for is to find the new harder problems. In other words, once we figure out, oh, this particular stem works well, or this is a great way to form this bulge, okay, now let's use that as, piece in something else. So the computers may be great at finding that, strategy market. The humans come up with the strategies. The computers are great at figuring out whether or not it's real or not. It's the hypothesis side. The third thing was dedication. That there are, say, people with family members with a specific disease. They can be highly motivated. But even, when I started in EteRNA, the dedication was from the dopamine rush. You got the points quick because you solved this little puzzle and it got you hooked. It's an addiction, and you guys have figured out how to get that reward sense. And with that reward sense, you get number 4, which is people are cheap. in large groups, crowdsourcing like this, there are a lot of people with time and interest, and they are low-cost labor. But they are self-selecting for the people who are interested, who are dedicated, who are willing to put themselves in. And so by throwing it out and making it wide open, you get access to that pool.
Very cool. I'm trying to capture these. I apologize. I'm like typing as fast as I possibly can because there's so many good ideas here.
Yeah, so I'm not sure how much new we have to say. I mean, I think you covered almost everything we've already talked about, but we definitely touched on that, people are motivated, especially if there's some disease that's important to them. But specifically, I mean, I think what's important to me is that, computer learning is really not there yet, and even if it was, it's extremely expensive at this point. And the thing I always think of the most is there was that Google recently, maybe it was a year back, used their supercomputing power to create a neural network that can detect like an image of a cat, right? And they spent millions and millions of CPU hours, and for something that a human can do so simply. So there's some things that humans are just very, very good at, and pattern matching is definitely one of them. And then definitely based on what we've seen so far, humans definitely seem to be very good at this, and I think it's definitely something to invest in.
Cool. Are there any? Okay, Are there any other groups left here? Oh, yeah.
So we're doing a kind of a chiming with some of the EteRNA players' comments in the chat.
Mm-hmm.
So Space Miser says that it also it defies traditional top-down organization structure. So when you're not worried about being fired, you're more likely to voice new ideas. So that kind of breaks.
I love that one. That's please hit for me.
Yeah.
I'll try to capture all of that.
So Space Miser says defies traditional top-down organization structure. So when you are not worried about being fired, you're most likely to voice new ideas. And then Nando says,
I'm worried about getting fired.
So the players are. Nando says, it seems to me that the only thing that venture capitalists might be interested in here would be that they would control the IP created in order to benefit from it. That would be a long shot since it would be a bet on IP that is non-existent at the time of investment. So anyone want to comment on that? They see taking risks and on non-existent IP.
Well, I think one possible answer to that comes from Sean's comment, which is simply if you believe that it's economically viable, then do it and make money, and then the proof will be in the pudding. But yeah, it's an interesting bar, and it's a different bar than we've sort of considered, and it's not. And I think it's sort of an interesting exercise. Yeah.
One of the things that we briefly touched on, and I think it's important, is that if you look at large pharmaceuticals in the VC community, they are looking for profit motivation frequently. And one of the opportunities I think that EteRNA has is the ability to be able to go after diseases that have a small community, important community, but very often financially unviable. And by having this kind of community, we have that opportunity to go after this. The other thing that I think systems like EteRNA offer, and I don't know that it's been pursued yet, but it's also to be able to start asking questions that computers will never be able to do very well, which is the ability to be able to ask, should we be going after a particular kind of research? Going after the wisdom, not just the time to do it.
Yeah.
Should we do it? And with a large community, you can start having those kinds of
Yeah. Yeah. Cool. Well, we've only got another minute in my session, and I guess I have an answer to this as well, and I think it's in some respects covered in this set of answers. And I really love the notion of the fact that humans bring not just problem solving but wisdom to the whole project. And I think my answer is really that it is about the people, and in doing work, we're not only solving problems as disembodied minds, but we're actually voting for these problems, and we're allocating our capital, and we're inspiring others to think about these problems. And the work that we're doing is incredibly unique, but it's sort of force multiplied by its effect in society, and that's something that humans do that computers don't do at all. And Riju and I once went on a long walk. I recommend getting to know Riju if you like to walk, because he likes to take long walks. And we said, what's really the most valuable thing about EteRNA? Is it the code or all the experimental data? And we concluded that all that stuff is ephemeral. It's the community itself. That's the totally unique thing that's irreplicatable, basically, and it has to be kept alive. So anyway, really, really inspiring, and a lot to think about for the rest of the day. So thank you guys very much, and looking forward to the rest of EteRNAcon.
Just take that chair.
Yeah, I'll share this.
Does your video have sound?
It does. I mean, some parts. It's like a whole movie. You can Were you able to get it?
I think so, yeah.
Okay, good.
Yeah.
In 2009, as I discovered, as I did research. Because EteRNA has no historian yet, so this is the first salvo at EteRNA movies. It focuses more on history than it does on what's the latest thing. But there's some occasional late things there, and I'll be working on it. It's too long. It's 9 minutes. I was signed up for 5, so.
You're an organizer.
I think, yeah.
You can have room.
I think we can go a couple minutes over.
Well, we built in 5 minutes.
5 minute
passing time, which we're going to consume. So, yeah.
Gee. Oh, wow. Where did you guys get that?
Looks like folded.
It is folded.
No, it says an RNA.
It is, well, yeah. If anyone wants, I'll tell you the story behind that.
Game enabling you to contribute to important scientific research. In this video, we will use EteRNA to solve the puzzle of man. Your mission is to fold the RNA into the target shape using 13 or less GC or red-green pairs. The control palette is located at the bottom of the screen. You can use the zoom controls to zoom in or out, or use the keyboard shortcuts plus or minus. You can click and drag on the screen to move the RNA. Now our aim is to color the RNA bases. The color palette highlights 4 different bases that create different bonds. Let's start with the base G, or red. I'm pairing red and green together because they create the strongest bonds, as indicated at the bottom. You can either click one time to color a base, or click and drag to color a whole line. The target mode indicates the final shape of the RNA. The natural mode indicates the current shape. You can switch by pressing the buttons on the bottom or by pressing the space bar. Blue and yellow also bond together, but not as strongly as red and green. Red and blue is the weakest pair. There are too many GC pairs in this RNA as indicated in the box. Therefore, we have to change some of them. We have folded the RNA into the target shape. Congratulations!
Wow. Where did you find all this stuff?
Some of it, if you don't know, there's something called archive.org. So that's one of the places I used, as well as YouTube.
The Internet Archive.
Yeah. Way back when she had a little bit on it.
Every lab round has 3 steps. Step 1, players design solutions. Step 2, the EteRNA community votes on the best solution. Step 3, our lab synthesizes and scores these solutions.
Wow.
At the end of the round, the top voted designs will be synthesized. Many players ask how should they know what they should vote for. Honestly, we don't know. However, that is the exact question that is being asked by EteRNA. Together, EteRNA community will discover the secrets of RNA folding.
Yeah.
This one
I'm being nice.
If you're worried about the role of technology in our lives in the future, you might be concerned about video games. Worldwide, people spend billions of hours per week playing them. But if you think that's a colossal waste of time, then you haven't met computer scientist Adrian Troy. He wants to make all that time and energy we spend on video games count. He believes that in the future, our obsession with them could help solve some of the world's biggest problems.
Think about Angry Birds. You will play that game 3 million hours a day. If we can produce a game that benefits society. By the way, when they were recording this, they kept on saying, speak more slowly, speak more slowly. So, and then when my parents out there, like, why are you speaking so slowly?
RNA. Once again, computers weren't able to solve the visual RNA folding puzzles. Rishu thought people would be better and faster, and he knew exactly whom to call to assemble his workforce. Like proteins, RNAs begin in a long chain.
And then self-assemble in beautiful, complex shapes.
Again, their shape determines what they do in our bodies, from forming the genetic code of some viruses to helping to create other molecules like proteins. So, if we can figure out how they're structured, we can fight diseases.
Understanding how RNAs work is critical for understanding life and for defeating diseases like AIDS and influenza.
With RNA, there was only one accurate way to tell if players assembled the puzzles properly. Make the molecules in a real laboratory.
And we realized, oh wow, that's the game. When you hit submit, we're actually going to make the RNA, and we're going to send you back the results. We're like, this is going to be so awesome. There's nothing else in the world like this.
Under Adrian's guidance, his graduate student, G. Lee, transformed their vision into EteRNA, a game that would be played by humans, scored by nature. People would be scored by how well their molecules folded in real life. In 2011, they launched EteRNA.
It just came alive.
is as if someone had just flipped the switch and turned on New York City. And we were just like, I think we did it.
In the lab, they synthesized the molecules the players designed. They looked like stable shapes in the game, but would they fold like that in real life?
And the results come back, and it's basically nothing. What happens when you create a game and you tell everyone we're all going to do science together, and then nothing comes out?
None of the RNAs folded into stable shapes in the lab. Adrian worried Eterna was a bust. But what he didn't count on was the community. Eterna let the players see data on how their molecules had actually folded in the lab. The chat forums lit up.
They'd all start talking about data. They'd analyze it to pieces.
Hundreds of players were discussing their mistakes and revising their strategies.
It was like the very beginnings of science. It was almost like when alchemy was slowly turning into chemistry.
6 months in, they plotted the players' progress, and Adrian saw a change.
And it was just like, the players have learned how to fold RNA.
That's pretty cool.
Wow.
Latest millionaire. That's it.
Wow.
And the mic for a second.
The mic.
So one of the things I learned was that you can't summarize Eterna in 5 or 9 minutes now. That there's an enormous ecosystem happening, whether you're doing scripts, or you're doing puzzles, or the lab, or you're thinking of hanging out on the development server looking at new things. People are experiencing lots of different aspects of a larger experience, and it put me a bit in awe. So I tried to do just a tiny piece of it, but there's really a lot going on, and it's also, I think, an invitation to people both here and online to check out the parts of Eterna that exist and they aren't participating in, or we as a community aren't using perhaps to their fullest. On to the next section.
And Leonard, you maybe put together.
That's the zero video editing skills.
Yes, thanks so much.
Yeah. That really was amazing.
So
Can we put a copy of it somewhere?
Yeah.
I would like to invite the next panel to come up here in the front. It's James Lee, Leonard, Jay Esselman, Johan and myself, I'll be there. We'll be here, and we're the speaker. The next speaker is actually Salish, who's going to join via chat, via Hangout in Europe. I'm trying to see if he's not in the live Google Hangout yet, though. So I'll have to convince him.
Yeah, I think we have to start PM here.
Yeah, PM.
That's a good question. I don't know the answer to that.
How the world supposed to sit here?
Yes.
Okay.
Yes.
Yeah, I guess.
So we're So I'm calling an audible here. So I'm inviting Jennifer Pearl to take my spot because she actually has some tools and has a better background in analyzing data. And we're going to let her speak as well, and I'll fade back into the audience. So.
Hi. So I've been away for a couple of years, and before that I was working on developing tools for analyzing the account loss. There's ways that we can try to predict how successful a statistics will be. And one of the things that I came up with is a tool. I can demonstrate it. I have my laptop here. I'll show you guys later. But it.
You want to bring your laptop here?
Yeah, can I do that?
Yeah, sure. Just. Yeah. Any word from Salish? Okay.
Is he on chat?
He was in chat. He said hi.
I'm not allowed to join the Google Hangout. Why?
What?
Why?
Wait. Oh. Oh, there it is. Do you have a HDMI?
Yeah, HDMI.
Actually, VGA. This is not.
That's HDMI. No, that's not. No, that's TVI. That's TVI.
Oh, here's VGA.
So Ray just joined us first. Okay.
That was me, sorry.
Oh, okay. No?
So I can put this tool on. I can put this on another computer real quick.
Okay. Maybe can Salish go and then we'll sit up here?
Yeah.
I don't know. He's saying he's not in.
He's in a hangout though.
I know.
Y'all just click on it.
Yeah. Can you email it to me? Or
yeah, I mean, it's clearly here.
Yeah.
Can you invite? Do you know how to?
Yeah.
There is it. There it is. Right?
Oh, I think I see him, right?
Yeah.
There we go, Lars. Okay.
So now I hope you can hear me. Can you hear me?
All right.
All right.
There's Lars.
Yeah, can you hear me?
Don't hear him.
We don't hear you.
Can you hear me now? Anybody?
No. We don't hear you. Oh, really?
Can you hear me now?
Yes. Now we can.
Ah, excellent. I hope the sound is reasonable.
That was me. Yeah. Let me.
Are you still? Can you hear me?
Okay. So, can you share your presentation, or do you?
Yes, I will. You hear me now?
Yeah, there we can.
Excellent, excellent. All right. Yay. So, can you see the presentation? Is that possible?
We can see your computer. We can't see the presentation.
No?
No, just your computer. We can just see like your browser, your like Explorer.
Okay, it doesn't want to do this. Okay. Let's stop this for a second.
Oh, okay.
Yeah, this one should work now. Excellent.
Okay, yes.
Yoo-hoo! Well, I do apologize for those 5 minutes. I was actually in Tsunamis Google Hangout, I think. But now everything works. You can hear me and you can see the presentation, yeah?
Yes.
Yeah, it's not in presentation.
Very good. Okay, well, first of all, let me thank you very much for the invitation to this event today, and thanks for all of you for organizing this, especially with somebody halfway around the planet from you. And thank you for the invitation for giving this this talk. I didn't really think I did that much, but okay, I'll try to convey a little bit of the stuff that I've done over the past months, years, whenever I found some time to work on the Eterna. So I give this a little title saying Eternal Trials and Tribulations, and essentially I will focus today on the Viber switch findings by all the designers or users of the interface. My name is Lars Rose. The handle is Salish99, which comes from the fact that I have been living quite a while in Vancouver, and so I got a little introduction about me here on that page. I'm residing and I have a background in Europe, and as you can hear from my funny accent, I have a German heritage.
We can't. Are you sliding to your slide deck?
Yes, I'm on slide 2 now.
Okay, we're still on slide 1.
We're also in.
And you're not.
Okay, this may take a little while.
To us.
Yeah, he's probably sharing the wrong window. Yeah, you're sharing the window, not the screen. You're probably sharing the window, not the screen. You want to share the screen.
Okay.
Okay. Yeah.
That's good.
Okay.
Yeah. Okay, that's good. Good. Okay. Good. Then I leave it small. That's fine. Alrighty. So I hear a little bit of an echo. I don't know exactly what you hear, but let's see if this works a little bit better. My connection is very slow, so I hope you'll be able to catch up with what I'm saying here. I've got lots of backgrounds in cells. I did a PhD at the University of British Columbia in fuel cells, and I've done research and development in skin cells. So lots of DNA work that I've done there, and on peptides. But I'm not really an expert on RNA, so whenever there's a tough question coming, I'll just refer it to my panel, and then they can answer all the questions for me. I wish I could have said that during my defense. But anyway, I have twins at the moment, so you can see them here, and I'm very busy. And also, they're with me at the moment. In fact, I'm not at home. I'm in this city that nobody can pronounce, called EteRNAcon, and that's the view from my window almost. So I'm on vacation at the moment, so it's even better that you invited me here. But my internet connection looks like this thing on the right side. So if anything doesn't work, blame it on this cable connection that I have here. It's rather ancient. So now what I'm going to talk about today is a couple of things. First, how do I approach a switch puzzle? making, and that's on my part, not the best ones, switch puzzles in the first place, using the tools given that you've developed, how do I do results analysis, and then what happens in the data analysis and beyond. So I'll go a little bit into this. Introduction, I think, is fairly common, fairly standard. I won't go into it too much. Johan Andreasen has made a really nice presentation. I put the link here. I'm sure you'll allow other people to see these presentations later. So just use the link later. But in essence, we're talking about these ribose switches. And in vivo, for example, in bacteria, they can turn off or on gene expressions by the way some aptamers are being adapted or connected to the molecule. And in this case, what we're specifically looking at is the FMN, the vitamin B derivative. And specifically what we're looking at is the folding in RNA using the straight FMN. What I usually look for is a couple of things, so 5 things really. First is shape, and I look back to this quite a bit during that talk. As far as this predictive capability allowed by Eterna, and I'm looking at does it really fit the shape it is prescribed? But even if it doesn't, sometimes it looks to me as if we could use it in the first place anyway. So is it still worth creating this molecule? I usually think, of course, it's my design. But I really try to even go beyond what the Eterna database or tool prescribes. For example, and I look back to this later, is some A purging fats. So how can we do reduce the adenine content in our molecules and submit them anyway, even if they don't look good in the software? So that's one of the things I look for. It's in shape. Next one is the energy difference between the states. So of course, in switches you have some energy difference between the on and off switch, and I try to maximize as far as I can. And there was some discussion online if we use Vienna 2 or not, and I don't really use it all that much. I try to stick in one of the 2 predictive tools that we have. And why do we do this? Actually, it's very simple. It's if I switch between those 2, I lose all the history, so I kind of go back, and I kind of like the ability to go back in my what I've done before. So not really the best reason, maybe, but I like to keep everything that I have in one of those predictive tools, and either Vienna or Vienna 2. Next thing then I look at is team building. I try to divide my submissions about half in what I do myself, so some original design, and half of adapting some really good designs by others and modifying them. And then we have something that turns out in some of these microRNA that is a mod of a mod of a mod of a mod of some other players. So this is what we have in those in those progressive experiments where we repeat in experiments again and again, and I really like this. Now what I do is somebody, I think it was Board, I can't remember, but it was said that I did some strategic experimental series. I really like that term. That wasn't my intent in the first place, but what I'm looking is, for example, just varying the tail ends of RNA, and it turns out it changes things much more than I thought originally. So, for example, there's a series of 16 where I have first the A at the front end, and then all the others at all the other bases at the tail end, and then vary that through. And it turns out that about half of them are more or less the same in energy and so forth, and the other half could be completely different in shape, in the energy that they have, in the free energy. It's quite interesting how different they can be, even by having such a small change at the very end of the molecule. Something else that I do is I do gradual removal of individual bases. So, for example, if you want to reduce the overall percentage of adenine in the molecule, the maximum to the minimum, of course, then it's really interesting how fast everything changes in that molecule. Just by changing 1, 2, and then 3 bases out of 100, 105, and things change quite a bit. And then finally, I try to introduce features that I thought worked well. So it doesn't necessarily mean they do work well, but something that I thought worked well. And that's where the online discussion is very useful, because then other people tell me, no, you're walking down a blind alley. You aren't going anywhere. So for example, I found out, or I thought I found out, that we have a hinge then somewhere in our molecule where we have 4 subsequent A's, and that works extremely well. So I try to reproduce that later on in repeat experiments, just to find out if it really does work well or if I'm just blowing air, essentially. So let's take a look at the next slide. Making a switch puzzle. This is my not very good attempt of making a rather good switch puzzle, and I think somebody on the chat that said they're afraid for the self-esteem of the people submitting bad puzzles. Don't worry, I'm not. But out of the, I think I made about 20-ish proposals for this FMN Synergy switch creation pool, and none really worked well. So even if I had a very high delta in binding energy, so 4.7-ish, close to the maximum that we calculated, it didn't really work out that well. So I just mentioned this here. I'm not perfect. I try to be, but it was a very interesting endeavor. But I didn't really get there. So I try to focus more on the data analysis that comes out of there and on the tools given. Now, one of the things that I would like to thank you all for having created here is this interface tool of the data analysis. Now, this one is taking out of an old design where we actually get shape data, and I really like this. So I looked at every result of these submitted molecules that I've had in the labs to see how can I improve them later. Now, unfortunately, with most of the labs, they run once, and then I can't really apply the learned things in the future. So I really would like to apply this a bit more, and that's, I think, where the RiboSwitch experiments come in and are very useful, because then everything you learn can be improved in future references. So maybe also as a hint for future labs that are running on shape data, run them again just to see if some of the learnings can be applied. So essentially, I look at all these results in the interface, and then I see exactly, well, okay, this was a GG at the 1 and 2 position. Okay, I have to do something about it. I need to change this. So that would be my learning out of this particular intrinsic frequency lab. So now I've talked a little bit about these RiboSwitches, and the design essentially there was we have 4, later 5 and 6 exclusion targets where the RiboSwitch turns off. So either the FMN or the MS2 bind exclusively at at sort of pushing each other out, or we have 2 same state molecules, or targets I should say, where one, or the MS2, increases the MFM affinity to the molecule. Then we share all these results with the RNA designers, i.e. us, and then we run subsequent rounds. And this is really the big draw of this particular experiment, because we can improve on everything that we've done before and make it a little bit better. And we can see, I'll show that on a couple of slides, that we really do improve. Now, of course, I'm most interested in how did my designs fare. Turns out some of them fared quite well, and some of them fared very badly. So in the first round, we all submitted some designs that were all over the board. And then from that, we took round 2 all the learnings that we had, and we had 1 perfect score. And there was this submission here, the SS2 1101. And from that, we went into round 3. So we had all these designs here listed on the left by a couple of people that worked really well by making small changes or by submitting some new ideas. But also, I found that taking this perfect result, the SS2 1101, I could completely screw it up and make 0 out of 100 points out of this with this particular design. So just by changing around a couple of bases. So it is possible to learn and to apply those learnings, but it's also possible to totally destroy everything that you have before. Now, for me, it's most interesting are these ones. Why did this not work, and how can I improve it to not have the same problem in the first place. Now, if we look down here, we have a screen print of all the data that you get out of the data analysis, but it's a bit limited. The GC pairs, UA pairs, GU pairs, they are just predictive tools. We don't have the actual shape data, so this I can't really rely on. And then from the melting point, the free energy, doesn't really tell me much. I just know it neither folds nor does it seem to be doing anything else. So this doesn't work well. So I need to go a little bit more into the data itself. And now I'm going to talk what I do to go through all this data. So let's look, for example, at this one. The best chunk of data I've ever chewed on was Johan's DDR8893. That's the RiboSwitch Labs, I think 1 and 2, rounds 1 and 2 or 3. And there were more than 12,000 points that we can really chew on. And I looked at the data, and first I tried to get an idea of how data looks like. So I ran it through some stat tools. And in this case, you can see this is a box plot, and everything that's in these blue boxes at the bottom is essentially one standard deviation of the data. This means that most of the data that we have is actually outliers, or considered to be outliers in my definition. So that means we have a wide spread of data that doesn't really necessarily conform to a standard deviation. Is that a surprise? Not necessarily, but it was interesting for me to see, because that automatically also means I can't really comb all the data in a way that I'm used to. So this is always the first thing I run through. How does a stat look in the data set? Then I've done some other analysis, and we can see this here. For example, I tried to see the difference in the change of affinities in the MS2 between the on and off states, and that's here plotted on the x-axis, the DDG, and relate that to the folding score, and maybe see how do they relate? Could I tell anything out of it, and can I learn something? And in this case, well, it doesn't really tell me anything. It's like some lady. This is, by the way, from Brothers Grimm. If you don't know who Mother Hulda is, somebody is shaking out the feathers, and they just fall down from the sky. This doesn't tell me nothing. But if I go to the next slide, now we look at the actual difference in free energy of the binding of the FMN and relate them to the EteRNA score, and we overlay them. Now, of course, the highest scoring labs I've put here, so if you want to find out which ones they were, you can follow those numbers. But if you ignore this, we can see essentially two peaks. And I tried to make it this little V in here. I don't know if you can see it all that well, but we've got this dip in the data in the middle, and the difference in between those two peaks almost correlates to the MS2 binding energy. So we can directly out of this data extract already information and get some information of whether our assumptions are really correct. Do we get this what we're looking for here out of the data? Is the binding energy really what we assume, or is it maybe higher or lower? So there was some good discussion online that maybe that there must be a slightly different value for the binding energy of either FMN or MS2. Then, of course, there was a new question asked of how can we improve the automatic EteRNA bot version 2 or version switch, I guess. I don't know how you call it in the end. And for that, I use these kind of graphs. I also have them for base pairs, essentially, but maybe I should bring that to the front here. And you can correlate the individual bases to the score. So how many bases should we have to have a good score? And for that, I made this little overlay. So essentially, in this entire box that we have here, so from say from 10 to 30% or so, we have really good results in the EteRNA score of the 16. Then adenine, same thing, and we see it's a very broad range across which we have very good results. So this is one thing that we can now use to interpret our data and to apply this in the future. But it's not narrow enough for my thinking. So if there would be only between 22 and 23% guanine content, then that may be advantageous. but it isn't. So there's a rather large section of these spaces that have an influence there, or have a good result. That also means that shape seems to have a much more crucial influence on this on the molecule and how it scores. So how do we get a handle on the shape? Very tricky. So we don't have the data ourselves, so I need to rely on essentially on the Vienna scores, on the Vienna prediction of how the shape looks like, and get some idea out of this. I'll talk about this later when I go to my quad A hinge. Now let's take a look at the data analysis. First, something that we saw, if we relate the content of N9 in our system to the number of clusters that we get, essentially how much yield we have in our experimental results, we see that towards very low A contents, pretty much almost as low as we can get by having that as a mandatory attachment point for the MS2, then we get a much higher number of clusters. So the yield is higher, and that also means that, counter to what we thought before of how to improve our experimental results to get higher yield, we need to go to lower A. So that's one of the experimental results that we had out of these experiments. On the other hand, I tried to get the same thing out of, well, maybe the DDG could have some influence on the number of clusters, and it turns out it doesn't really. So this again looks like some kind of random cluster of data put on top of each other. So it doesn't really tell us very much. But this one is a very clear indication that we need to change something in our experimental design if we want to increase the yield. Now, how much do we need to change to be still sufficient in our data? That comes on the next slide, where we thought, okay, how do we determine an acceptable number of clusters based on the fold change error factor, and where should we set it so that we can say, okay, this is really good data, or this is something that we have to ignore in this particular round. And this is not set in stone. This line that I put in here, it can be moved up and down. So essentially, how many clusters do we want to have to be sufficiently convinced that this is the data that is accurate? So again, I put it in here, and we calculated that this is about 30% of the data that we have to throw out that has too low yield, under 10 clusters. We may also decide that that's too high an assumption. Maybe we can live with 2. So that's still open for discussion, but I just wanted to throw this out here. Something else then that I looked at is at the dissociation constant. So essentially the log of the free energy. And we typically have a very low cluster yield. And I wanted to find out whether there is an ideal dissociation constant.
Oh, hey, Salish?
Yes?
So we have a few minutes left for the actual talk, and we want to like, give the panel like kind of like open it to the panel for suggestions and comments, and as well like Jennifer Pearl wants to present one of her tools. So
let's go. Give me 3 minutes and I'm through.
Okay, sounds good.
So essentially here we have this precipitous drop of the KD value. So at that I thought, okay, at least we have some indication of what happens here, but it doesn't really relate to a number of clusters. So if you can see, this is almost the same value all across the KD values. Something else that we found very interesting were these 3 hockey sticks. So we correlate the F max values, essentially the medium of all the maximum clusters fluorescence, and normalized by the standalone MS2 hairpin fluorescence. And then if you have a higher binding energy, that may be going towards saturation, but we find that we have significant increase in Fmax in the low score regions, 0 to 40, then a slight increase, 40 to 60, and then pretty much no increase from 60 to 100. This means once the molecule folds really well, it doesn't matter what kind of switch energy we get out of there. So it was interesting to see that there seems to be little or no influence of the switch efficacy on the score of Fmax. So that was interesting to see. Now, if you go beyond the data analysis, essentially we can look back at the shape, and I put it in here. If you go back into the presentations, you can see how this looked like, but it's based on the Vienna Vaughan predictions. We don't have shape data. Also, and I hope some of the labs there can be tested for shape data later. What I would like to get is, or what I would like to thank is all the people that participated in the talks that we had online, everybody listed here. That was very nice to see. Something else that I go through very quickly is now the microRNA findings. And I thought, essentially, good designs that we had here sometimes had this is an external microRNA that we attach to our molecule. And I thought that there seems to be an affinity for 4-string A section. And I've indicated it in these errors here. I won't go into it into too much details. But in the online discussions, we found that first, both straight hairpin attachments and band microRNA attachments across 2 hairpins work really well. And we have all A's in this 4-string A in the microRNA. They should be attached to a U. You can't really have them bridge something else. That would be a low score. And I was trying to find a good reference how you can bend this RNA. And I found something on DNA. It's not really well related. But for me, the idea is if you have 4 A's in a row, does this bend better than just having a AAGG? And that was kind of my result in this particular experiment. What happened is if you have GC-rich designs, they don't fold well. Okay, that was no surprise. And we have a broken 4-string A, have a GGAA, like in this case. It doesn't work well. And if you have no dangling A's in this position where the microRNA attaches, that also results in low scores. So for me, it's still something to look at. Does this really work well? And this is what I'm trying to do in this repeat experiments. We can now try out how they work. So to sum it all up, first of all, EteRNApackage is a very good tool to predict how to really how RNA folds, and we can use it to improve the accuracy and precision of our RNA folding. And the findings by us essentially can be used to improve that, not only towards the goals of the Feynman challenge, but also to improve fundamental understanding of RNA folding in general. So I really like that idea. With that, I would like to thank you all for listening. Sorry it took a while for me to connect. This is, by the way, not from my home, but it's very reminiscent of what I'm going through at the moment. So with this, I'm opening the floor for comments and suggestions.
Thanks, Salish. We'll have Jennifer set up her demo now. Meanwhile, any comments or questions, from the audience?
I'm the only one between you and your lunch, yeah?
There we go. Hello, Lars, can you hear me? Hello?
Yes, I can hear you.
This is Riju. I'm just asking a question while Jennifer's setting up. Thanks a lot for giving the summary. That was really useful. I have 2 questions. One are very short questions. One is just some of your suggestions were. One was to rerun the high throughput shape RiboSwitch labs. Is that right? So you would value, there was a set of labs that we ran in 2012 with I think 12 different RiboSwitch designs that were tested by shape and mapping. So was your suggestion then we should iterate on that? That would be useful. Hello?
Hello?
Hi. Okay, good. Let me just repeat the question. I just wanted to understand some of your suggestions. One of them was to go through multiple iterations. So, in your opinion, it would be valuable to you want to repeat certain labs. Can you just tell us which labs you thought would be worth repeating?
Yes. So sometimes we run a lab once, we get a result, and then it never comes again. So I don't know why a particular lab worked really well and why it didn't. Because then I can try out whether what I think worked well really did work well or not. So just.
Are there specific labs that you think would be valuable to repeat?
Yeah.
Okay. Maybe you can send those to us so we would know, or we can ask other players what they would find valuable. Another question I had was, you alluded to finding some designs that had really good scores with lots of A's, but they didn't make it through the census pipe. There were only 2 clusters in the census pipeline. So that's something that you or other players feel is the case, that we really should work hard to get more designs with lots of A's synthesized, that there's golden designs there that we should be trying to synthesize.
Yes. Some of the results that we have, I hope you can still hear me, I cannot hear anything. Some of the results that we had indicate that there's a super high yield or a super high score, but we don't really have the yield. So maybe it's one cluster. So I can't really consider that a good result, because I'm not sure if that's a fluke or an actual result.
Designed to be 40 or less. Yeah. But you can still submit above that, which is good.
Yeah, right, okay.
Yeah. I know Lars was saying that, where is it here? Oh, that he looks for the sequences that fit the shape and fit the energy bounds. One thing that I've noticed is that winning sequences don't always do that. And in fact, he had in some previous rounds some shapes that he put in that he thought, oh, well, this looks interesting, it doesn't fit the model, and it scored 100. So, you know, we need to be careful there in our expectations and look at the energy models we're using, and is this really a good fit to what is, you know, in vitro versus in silico? That is a good question. Also, we're somewhat drowning in data now. I'm ever so thankful to whoever came up with the idea of fusion tables, because that's given us some sanity.
I think that was me.
Yeah.
Probably here, right?
Yeah, unfortunately, the tables that I make have so many graphs, I cannot put them in fusion tables. It doesn't like it anymore. So I'm sharing them through Dropbox, but that's rather tedious.
Yeah, Lars is saying he can't share things through fusion tables. He's doing it in Dropbox. But if there was something we could do, also he talked about, you know, the shape data labs. I really miss those. I mean, I love getting, you know, thousands of results back, but you can't really tell when you've got like the on and the off, and that's it. It's a little bit harder to tell, okay, so what should I be doing differently? So if we could run occasional shape labs, and another thought was alternate 2 lab streams in alternate months, so that you've got, we submit the lab, it takes a month back, and meanwhile you can be working in the alternate stream, and then you've got a month to look at the results after they've come back before the next round is due. So we've sort of started.
What I would also suggest is take one of the of these large driver switch labs and use the best 10, 20 designs and make them into a shape lab.
Yeah.
That's a great idea.
So try taking shape labs from the better shapes.
Yeah.
Anyways, if there's something that can be done to help us sequence through the lab results.
Hello?
Run through them.
So I think we have a document that Eli and others have compiled about how to improve the lab interface. Where you just suggested is an interesting one. I hadn't heard it, which is to allow 2 to show up on the same screen. Is that the idea?
Well, I mean, sometimes comparing two could be useful, but I'm thinking if you've got, 100 designs that you want to run to be able to use left arrow, right arrow, and just zip through them instead of having to go back to the menu, select next, or jump back.
This will come up again tomorrow. We're going to have a whole discussion on feature requests.
So this is the trials and tribulations is why I'm putting it in here.
I just want to really. Oh, do you want to go first?
Yeah. It looks like Jennifer's
Yeah.
So one of the things I was intrigued about was how much I was learning just watching the statistics that Lars had put together. And what I was asking to myself was, what forum do we as a community have to regularly look at findings, share them, challenge them, learn from each other? And I'm not talking about dev chats. That's nothing like that. So it seems to me one of the things we should be prioritizing is adding a cadence every week or every 2 weeks or something like that, where the community gets together and schedules 15 minutes for someone to present, and then 45 minutes maybe or something like that, where we ask questions and learn and speculate and generate new ideas.
Good idea.
Yeah, well, that's definitely a super good idea. I mean, the thing that I definitely want to follow up on, like what Lars was saying, specifically his one switch where he changed that one base pair and he went from 100, it turns from 100 to 0. I think cases like this are definitely something we need to investigate with shape. And assuming that it wasn't this like low cluster or something, is actually a real result. I mean, these are the types of things that we might never have known about, but someone just decided to try it. And I think these are some discoveries that discoveries in the making to get like more detailed understanding of like how these switches are actually working. So I think that's exactly like what EteRN is about. So definitely be good to investigate.
Yep.
Okay.
Yeah.
Good. Oh, so this turns on.
Hello? Alright, so to start over again. So I've been working on coming up with a method for looking at dot plots and being able to use them to predict successful synthesis. And I came up with this tool. It's there was this program that I was using called ImageJ that allowed me to do a red dot overlay with the dot plots. That would give me a relative value of like how well what the pairing probability is for a Pacific tide or the lake. And I'll just demonstrate it real quick and explain a little bit more. So you set the capture area, just do a rough capture area because it auto calibrates so that you can. My goal is to have this repeatable and reliable across different people's computers, so that this can be actually used at more than just one computer. And just good engineering practices is to have a good repeatable and reliable method for analysis. And so you set your capture area, save, and then this is what the area looks like right now. You can do a auto size, look at it again, and now it's got the correct balance and everything. So you go into your analysis and capture your dot plot, and then just display it. And if you've if you've seen any of my papers, I came up with a value called the intensity threshold value. That's actually straight from ImageJ. That's the value that they referred to this as. And so what happens is you get this red dot overlay, and as you proceed through the different values, the nucleotides turn red. And so this is based on the for grayscale, there's a range of 0 to 255, which is actually stand for all RGB colors and stuff on computers. It'd be a long process to explain why that is. But So that's the value range on this, is 0 to 255. So it isn't correlated to an exact pairing probability right now, but that's next on my thing. And so what it allows you to do is you can kind of see at what value these different legs have a probability to pair at. I don't have that exactly correlated yet. But if you look at one of my papers, I found the graph. So if you go through and assign, sorry, I'm having a hard time explaining this a little bit. So it's a relative number, and I'm having a hard time explaining this right now.
So you have two different states.
Yeah. So you have your first state, your transitional state, which is what I used to call the intermediate state. The second state, and the terminus, which the terminus is what I am calling when you get to this point where it just kind of just all fills in.
Oh, I see.
Yeah. And so you got your first state. Okay, so with multi-state RNA, you know how on the dot plots you have your first state and your second state are both visible at the same time. And so that's what the first state and second state is about. And the transitional state is that little leg that'll pop up, and you'll be able to see it sometimes on multi-state RNA when you look at multiple dot plots alongside each other of high scoring designs. And if you reference look at some Eli stuff, he mentions that in one of the papers. And so you can see how there is somewhat of you can see a little bit of a pattern, and this was with a very small data set from back when we could only synthesize like 7 designs a week. That was torture back then. And I'm really excited getting back into everything now with the Cloud Lab, because you'll have so much more data points. And so there's going to be a lot more of this coming out in the next few months or in the near future. Are there any questions? Sorry if I was kind of jumping around a little bit, but I didn't really prepare for this very much.
So one brief comment is that I don't know if that one depth think of putting like a better visualizer for dot plot down the road, but
yes. Well, so one thing that I have ran into that actually is a question for the devs actually would be kind of cool is if we could get a dot plot that has like a set size where each input type is like 1 pixel, or a group of pixels, like 4 pixels in each, and they're all the same color, the same intensities, and then I could create a program that would walk through everything and really do like a really deep down analysis. Because one of the things that I'm working on is being able to actually have it go through and walk through the entire dot plot and pick out different legs and actually be able to say, okay, these legs are always here on these higher scoring designs, and that's where the future of this is kind of wanting to go with it. But I'm kind of limited by some of the stuff that we have.
What if we left just a download in CSV format of the base pair probabilities? Would that help you?
Yeah, if I had a text would actually be really good, because then I could just parse through that and crunch that really easy.
Nando's version of the Vienna tools that he's put his tweets on, you can generate the dot plot for yourself for any sequence, and then you've got the numbers in an array.
Oh, cool. I'm gonna check that out.
The panel, does anyone have any questions, comments, further? Otherwise, we have lunch waiting outside, and we can reconvene here at So we come in here at around 12:30. Hogbaku and JMF have some fun times waiting for us. So yeah.
It will also be live. Enjoy your lunch.
Will there be someone watching the room for reading laptops and stuff?
I think it's.
I can guard the room if someone gets me a sandwich.
It's probably it's most likely safe.
There's only one room door unlocked, right?
Yeah.
So just someone has to watch the door.
Yeah. Well, actually, there's two. But yeah.
Okay, I'll watch the room. If someone will bring me whatever we're eating. Okay.
Yeah, don't worry about it.
Thanks for listening.
That's cool.
Look forward to seeing it. All of the big
Somewhat.
Look forward to seeing that.
Like, somebody started developing computers.
Yeah. Well, actually, it's been.
Oh, okay.
Should I keep hanging out?
Yeah, sure.
Okay.
Should you talk later today? What? You should talk later today?
I think so. I think it's definitely. So I was just going to ask how I do with like file. Do we transfer the presentation onto here, or do we bring our laptops?
Whichever you find better. I think this computer's kind of dying, so let me bring your own laptop.
Okay.
It died.
I know. I saw it. It's something happened.
So in theory you can't because we needed to cater for them, but who's going to?
Oh yeah.
Yeah, I just screwed them. Like told you to.
only
okay, it's catering, and it's like double the price. Literally double the price. They charge like.
And all these things to apply it. You have an intuition. That's classic.
It's like if we can start to 150 more, it's like,
it's just even by hand. Look at the top 10. There.
Really? I'm so happy to hear that. This is the first time, like.
And we have a developer who is developing strategies for player-defined features.
Basically, this is the first time we're still like 3 weeks ago.
And he's coding them up. And if it's a baseball card, look at this feature, one that we I want this predictor. First of all, they'll test it on all 10,000 or 20,000 for you, 5 ratings for you, right? And report the correlation.
But it's crazy.
But then, and if it becomes like something that has some value, it will work maybe with you to make it much easier to see within the game, or even as a column in the table, for example. Like if you find that the your second threshold value, like for seeing the second state, is predictor protected, I think it might be.
Well, yeah, I saw some, like, if you look at it, there is.
We can just include it as a value in the table. So like, I suggest doing that. Just look at the top 10 or 20 for a puzzle, and also compare them to like the bad ones, for the mediocre ones, and then see if you can come up with a base for a problem.
I'll start working on that and actually looking at it, start analyzing and doing some.
Yeah, so this is a good time. Yeah, because we're trying to work.
Adrian, that was nasty. Don't hit the microphone again, please.
One of the things
Oh, I'm so sorry. Didn't know it was on.
It's okay.
Back when we were doing when we were doing and I just designed it to the DOS
They're running out of, not running out, but turkey, chicken salad, roast beef.
Actually, if you're going to go outside and chat outside with people.
You care for avocado?
Well, I actually think that like there's enough people here that.
Yeah.
I don't know which one I was using, but it,
Otherwise, I'll just sit here. I'll hold guard. I'll be guard. And Anna's gonna come back and you have turkey.
Oh,
If you want to sit outside, I'll be outside when.
Okay.
Okay.
And it's actually the multi-stack are kind of a problem. Like that it is.
Hey, so are you an Ethernet player?
Where all the energy models start. So if I go online, it's like those are options. It's like a gift pack.
Yeah, it's turkey for Cody. And then you may, would you prefer chicken or roast beef? All right.
Since you don't care.
Just wanted to offer it. I'm gonna go sit outside though, because it's more than starting.
What was the motivation for coming?
All this interest.
Yeah.
And that's not right. Yeah. I didn't mean to interrupt.
No, that's fine.
I drove to here.
A long way. You live in California or north or south?
Straight across.
Oh, straight across.
East.
Oh, you guys are east. Okay.
Yeah.
Very cool.
Yeah. Around the bay and around the mountain.
Oh yeah.
Not that far, it's broke flies.
I don't mean to interrupt you if you're in another sandwich.
Oh, it's okay. It's been a long time to eat it anyway.
That's true. How did you learn about China the first time?
Nova.
Oh, is it Nova? No. That's cool. That must have been scared for a second in the past couple of years.
Yeah, that was 15, 2012.
Back. We can go outside.
I'll just finish up this conversation now to have some people outside. November 2012. And what were, I'm really curious, what were your first impressions of the game?
Well, first, it was just kind of relaxing.
Game stuff.
Yeah.
Interesting.
Something to do.
Interesting. So were you more interested in it as a game or in terms of the science or both?
Well, when I started out, it was more as a game, and when I started doing the math, I like, oh, it's better than a game.
That's interesting. That's so cool. That's really, really cool. That's how it was supposed to work. But it's really, when we're over here, it feels like we're very far from the community.
Yeah.
And, you know, it's actually not that big of a team working on it. And so, we don't have like analytics departments or anything like that.
Right.
We're kind of guessing that it's working. I mean, we can see what's going on, but it's very difficult to see actually. It's a little bit opaque. But it's really cool to hear a story.
Yeah.
At least the one person who worked a little bit the way we expected or we hoped it would.
You know, I was doing it a whole lot, and then, you know, the last 6 or 8 months, there's so much going on in my life that I slipped. Made it up to 17, and now I'm back to 3.
Oh no.
Yeah. But I don't have that much to do right now.
Right. That's, I definitely know how that works. I'm also actually very busy time in my own life. And so it's basically been, actually a similar thing with folded stuff. With folded email, I was very involved in the creation of the email. Then eventually it became only the scientists. So, and similarly with EteRNA, I was probably much more involved in much less involved in and of course, my own life is still to do other things. All right, and are you gonna defend everyone's stuff? Okay, good. Well, I'm glad you're doing it because this is my precious computer right here. Anyway, really nice chatting with you, and I'll see you all day today, tomorrow. Hopefully.
Yep.
All right, thank you, Anne.
gotta write something down before I forget it. Okay, where is it? Out here. How come you're not there?
I'm washing off the laundry.
Ah, making sure, she's a thief up there. Watch her very good. She's gonna steal everything as soon as we leave.
Let's go outside. Enjoy the weather. Good idea. I'm here. Don't worry. If you go outside, turn left, you see the garbage bin, go downstairs.
Right by the garbage can.
Yeah.
Wait. I didn't see anybody. Let me take my phone with me. I might want to steal my phone. Actually, my wife wants it.
Do you not like to go outside?
to lunch.
I think they
Yeah, they're outside.
downstairs,
Yeah.
restaurant. They might also tour around the campus.
Yeah, your lunch.
I see it. I saw you can catch the train.
Yeah, we're like, run. Yeah.
I think that's good. The train is like 2 minutes.
Yeah, no, it worked out well, thankfully, yeah. Yeah, I was nervous.
So, do you get sick from food last night?
No, it was fine. It was fun last night. Oh, it was really good. God, so there were like these kids on the train. They must have been like middle school or something, and they were like going around like harassing people. Yeah. Like they were walking up to women and like trying to ask for their number.
There was middle school.
They ask for money.
Number, like
Number?
yeah, phone number. They're little
They
kids.
bored.
No, I mean anyway. So
So my mother-in-law, she drove quite a while last year, and she been harassed by the high school kids or elementary school kids. And then she's the old lady. Is like, oh, you guys have a walk, jump into her car, and they said, by the way, you have any money?
yeah.
So it's like, woman, they already give you a ride.
Yeah.
It's curious.
Yeah, well, I mean, I got very upset because that was bad. So they were two women in front of me and it was like harassing them, so like they grabbed them by the arm.
Oh, cool.
And I like brought him to my eye level, and I was like, hey, what you're doing is not acceptable.
Right.
And yeah, and I guess I scared him because he went back to his seat. Shut up.
Cool. You did a good thing.
I guess. I feel bad. I shouldn't have grabbed him, but it was so mean.
Kids have no manners.
Thank you for protecting the fort.
There's still a lot of personality.
It's all part of the plan.
Yeah.
Yep. Knew it. I knew you seemed a little too eager to pass on the computers.
Yeah, I think so. So I can get one like over my head. Yeah, there's one GoPro.
Fake it. Fake your tongue. It's true. No one will tell you to get no. You wear trucker hats and t-shirts and cargo pants. Probably fall off a little bit.
For a little bit, yeah. Or I can just steer and skid.
What's that?
You know, just give up.
Yeah.
Become, I don't know.
Or you could go the opposite round, just hard going to like 70 and
Yeah. You're like, whoa.
So good.
That's amazing.
Yeah. What's your secret?
Blah, blah.
Dude, I'm still starting to category theory.
What's that?
Category theory.
Oh, yeah, that's right.
Chubby type theory, the new foundations program. Pretty wild stuff.
So how are you calculating? How is it? It's pre-calculated ray tracing?
It's no, every single frame is pre-rendered. So the way it works is that.
How do you interact with it?
Oh. The cortex does follow. It approximates a complex mechanical system as a finite state machine. So,
okay.
And then, actually, in this case, the original way that we did this actually was for what? This is the paper that is off the top of the really cool. What? Yeah. So, here it is applied to water. So, basically two key ideas. One of them is that knowing something about this time position of the dynamic system and constraining the ways in which it can be interacted with.
Oh my god.
Yeah, all real time. Allows you to build, this is literally a finite state machine approximating a tank of water. With millions of states. Turns out you can capture a huge amount of nonlinearity in the context of a finite state machine interpretation. So there's two pieces. One of them is that you know.
Oh my god. Yeah, but states. The number of states.
Right.
It's puzzling me.
Right. This actually describes how you build a finite state machine. So basically, you, this is the whole thing. This is the whole thing about big data. Like, for example, to create this demo, we're paying Amazon $1.6 million pure compute. This is like 80 million core hours. See, like, people don't get how much compute there is now. You have to like change, you have to add like 6 zeros to everything. 80 million core hours. Anyway, so basically,
but it's all pre-computed.
It's all
pre-computed. So now you can do it anytime.
Yeah.
But how big is the file?
It's
how
like,
is it stored?
I forget all the words in that, but something along the lines of 100 characters.
AJ, what is this?
This is period stuff.
That's insane.
Yeah.
Yeah, but the carrying costs of all this are okay.
We've got all the models. We've got the business model. Well, the problem with the business model is that it's very. I mean, people don't usually have like $1 million lying around.
No.
And do that's a problem economically. It means anything you can do with this CD, you have an additional $1 million in return. Right. Relative to like the second best way of doing it, which could be like in real time on a GPU, but slightly worse. Right. So that's a problem, but on the other hand,
so, do you compare it to other solutions?
Yeah. And there's two. We have
That's insane.
We can completely characterize the error of the method because we actually know.
How is that possible? This is like a. It's like a.
Because think about it, it's a finite data machine. So every point, every vertex in this finite data machine is data. And every edge is every arrow is a transition. And we can also run a simulation for every state, which we do against lifetime cost and measure. And so we can measure the difference between where the state the arrow has to go to and the actual simulation state.
Yeah, that's super impressive.
And then the real key is you do it relative to a player model. So that's what this whole paper is about. Not only can you go
What's a player model?
Right, the player model is basically think of it.
We want to have a group photo. We got to talk about
Sure.
Yeah.
Where was the Zoom?
Your bottom. There's a cookie.
Hey, all.
You can have mine.
We're gonna have a group photo.
No, I already have it. I said this is my son.
Yeah. So yeah.
Okay, did you get everybody?
I'm rounding up from the people.
The player model.
Okay, so the player model. So basically, we call it a player model. What it is you go this way. You have a finite state machine approximation. Actually, in this first paper we run in 2013, we had the error. You literally start with here's the state. No matter what happens, you go back to that state. The whole water simulation is one state, just does the same thing over and over again.
Right.
And then you say, well, that's not a good thing.
That's terrible.
State, right? And then you add a third state and a fourth state, and then it starts growing this thing. We have a graph. The topology grows over millions of states, right? Interconnected, right? Approximation of the water. So then you measure the error, and basically it's a greedy algorithm. So basically says, given this, there's basically one operation called expansion.
Can you measure the error based on like a model of?
Hey, we need to do a group photo. So in the original paper, 2013, the error was the sum over every state, fractures over every state.
Right. Yeah.
I watched them.
Okay.
Someone has to watch the room. You're gonna watch the room. I would say, don't worry. Come on.
muy eficiente. Muy eficiente. Sí, le digo que.
Bioeconomics and RNA stuff. Computer science department.
Oh, well. I love that department. Really, really wonderful department.
I want to see the back.
His department's go, it's pretty nice.
What's that?
I say his computer science department's go, it's pretty nice.
Has a good atmosphere.
There's a lot of teamwork stuff done there.
You guys have like the AMP lab and the PAR lab, right? Yeah.
Worked with both of those.
Okay, yeah, that's cool. That's cool. Yeah, that's something that like Carnegie Mellon doesn't have at all. That notion of like these large scale labs like that.
Dave Patterson was one of the first to really push that forward.
Okay. Yeah, I think we fun to chat with you later today. I see like perfect academic computer science being like basically disrupted right now, like and it's no longer the place to do many things that it was years ago.
Well, that's the neat thing about places like Parlab and AmPlab, because you get industry coming in and mixing with you.
Yeah. 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 That's good.
They have like two retreats a year where the industrial funders come in and they talk to you about what research you're doing, what are your preliminary results, we thought about doing this, and so they feel like more involved in research rather than here's a bunch of money and at the end of 3 years they get a report.
Right. That's very cool.
Yeah, exactly. Do it really big.
Yeah, for biggest scale possible.
So there's a finite number of states actually.
Yeah. But there's enough of that.
You'll never see them twice.
Well, you actually might. You won't. There's a threshold beyond which you won't realize it. And
No,
in fact,
I certainly that's true.
And even if you do, I mean, there is ultimately, this is like a reason for the idea behind it. I didn't work on.
So
I always wanted to, I always knew that on some level there was a nanoscale. You know, this what was going on here. But we never actually really got but it would be so cool to characterize it's like that spires. You know, what did that look like? You had it like because like strange attractors or something. Yeah. So what did that look like?
Right.
And lay down early gas. Characterize and
as part of our argument,
where will converge to?
yeah. Oh, that'd be all the more reason then to kill a little time.
Not too much fun.
Which way is live?
Is this live?
It is. So, I'm going to ask you all for a favor. Because almost a professional table. So I don't know about your table, but our table had a really interesting, really enjoyable discussion about a lot of different stuff. We generated a bunch of ideas. Did your tables generate ideas too? Now, I'm not asking you to nod yes or shake your head no. We just chatted about fun stuff, not EteRNA today, whatever. Write down, right now, on the conference, take 5 minutes. Write down good ideas, things that you really wish would happen in EteRNA. We'll figure out somehow after the end of the conference, we'll put them all together as if we had a virtual sticky chart here. And we'll see what things we generated. I bet there's a bunch of stuff that we're all going to be thankful we went to that lunch for, and it wasn't just for the good cookie and good apple. Okay? So just give people a couple minutes. Write down things you learned.
And how much cookies? Well, that was so that's. But did you solve the state machine for?
Yeah, we do that. That is a video, but it's the state machine.
But and you solved the state machine for any the thing rolling any which way.
Yeah.
So that took a lot of.
Yeah. Actually, that turns out that only for this very thing, David.
3 hours. No. Oh, that sounds cool.
Yeah. The really expensive part is actually right.
Oh, so you do, okay, yeah, right.
And this is actually different from the actual the wire.
Right.
So,
whereas this is the ring.
Right. So.
How far away from fully dense?
I guess shows how you can really. This is actually one of the rational wire. This is sort of the picture of the topology of wire on the model, but it's not really understandable.
The right, like, there's that axis.
Yeah, it's not like laid out. This and then the question is, I would also have that last.
Oh yeah.
Because that's it. Basically, that's the right. Maybe the trade-off is that this sorry, there's going to have more restrictions on it. We can't go on all the way. But it's going to have like a level of graphics and also established. So we're hoping
You asked me because I was just I'm sorry. I didn't know. You're okay.
This is not even done yet. This is still like ideas in the process. Right? Like we have this is not standard. It's all of these graphs and all these.
No, there's no. There's a. Oh, you know what? I'll tell you.
Just the data, which is pretty. Yeah, we can draw on this. Lights would be good, I guess. I don't know where they are. Here.
Can we use these?
Yeah. Okay.
All right, you can start explaining it.
You got the categories. Okay. All right. So, welcome to.
Grab the mic.
Oh, yeah. Hello.
Hello. Turn it off. Just make it hard for you. Sorry.
How about this? Okay. Hello. Welcome to Fun Time. My name is Lee Bickle. My username is Hogalahoo. That's the supposed official pronunciation. If anyone wonders, according to the guy who coined it. All right. And you are?
I'm JMF 028. You guys can call me Jim. Right now I'm sweating like profusely. So if you smell anything, just think of a really hot stud guy that's like just having some problems. He just got out of a workout. Don't picture me because that'll just make it gross. So, but anyway, so that's the smell if you're smelling. I'll give it back to Hogalahoo.
Great, thank you. Okay, I need some help. I need 5 volunteers. No, I'm not telling you what you will be doing yet. Okay.
That for sure, LaRovi.
Yeah, you don't have to come down, but you need to like write the names down, right? I don't know. I'm gonna forget. We got 2 so far. LP6.
LP6.
I'm sorry. Tell me your name. I can't read your name. John.
That helps.
I'm sorry.
There's like 5 Johns. John/LFP.
And Mitchell, right? Mitchell.
Okay, so
Jennifer,
we got 2
were you
people.
Oh, I'm sorry. I thought I saw your name. Okay, yeah. Need 2 more.
So, Jen, you're going to be.
Okay. Yeah. Oh, yeah, Jennifer, we need 1 more. Oh, here, please. Or I will select 1.
Really? Come on.
Okay, so what you'll be doing, it's not hard. What you'll be doing is we're going to be asking questions, and the leader will extract a response from their team to give us within 15 seconds before my little timer goes off. So all you're going to do is give out a group answer. Go ahead, another volunteer to do this.
Here we go.
Thank you. And if you would do the honors of slicing the room
All right. Well, we can't do it much this way. There's only 2 of you. Could we have some people like separate into 5 groups? So
count off. Just start count off 1, 2, 3, 4, 5.
That's true.
Okay.
But first,
we need the leaders to pick a number.
Right, we'll do that after
Okay.
we count. Okay, so we'll go 1, 2, 3, 4, 5. Oh,
Are you only having a number?
we're gonna do 4, right?
Let them count. Believe me, they can count.
Let them count? Okay, let's start over again.
What's this? Is this
1.
like a co-leadership?
We're gonna do 4, right? We're gonna do 4 now? That's fine, right?
Okay.
2,
3, 4, 1.
3.
4. 1. 2.
3.
Oh, you're the leader. Okay. We'll go down until Ropi. We're starting over from 1.
1.
Okay.
2.
3. Oh, you're okay.
4.
2. 3. All right. So we have an odd number in 4, or we have a less number in 4.
4 will have to
Roy,
split up.
Roy, you 4?
He's 2. He said 2.
He said 2. Okay. I'm just trying to make it fair.
Roy knows all the answers.
Oh, Daniel, did we get you? Perfect. You're 4. Okay. So everybody who's number 1, we'll have you sit over here. These tables right over here, and then the split out point. We'll have 2 sit over here. Then we'll have the split out point in the middle of these tables. 3 are over here in this end, and then 4 is over here.
If you don't want to play, that's fine. You're just hurting your team.
Fine.
Where are the 2s?
2s are over here.
Can you tell us the prize?
That's a secret.
I'm not sure if we should do that. I mean, motivation might drop a little.
Yeah.
But there are prizes.
Yes, there are.
I kicked him out of
All right, is everybody grouped up? Okay. So we're gonna have you guess a number. We're gonna have you guys guess a number between 1 and 10. The leaders. Well, basically, it's who gets to go first. It's between 1 and 10, and the closest one to my number, obviously, will get to go first.
We already guessed.
7.
Okay.
Oh, he just changed his number.
Well, hopefully.
9.
All right. My number was 1, so it'd make it easier for me to group you guys. So you guys were 6, right? Or no, you were 7. 5 goes first. 5. So you're gonna go first. 6, right? Okay, you guys are gonna go second. 7, you guys are gonna go third, and then 4th, because you guys were 9, right? Okay, so that was a problem.
Well, 5 is always the best number. First.
Thank you.
I don't know. Whatever it is,
Where's Mitchell? No, there, right there.
They're backwards.
3 as well.
Leader of the pack.
Oh, Jen's group is 1.
Who hasn't said anything?
Mitchell's 3, right? You guys are 3?
I thought you were. Oh, yeah.
All right, no. What order are we going in? Are you 3? You're second. Okay. All right.
John.
Yeah, they. Oh, you hiding?
The mic is like. Okay.
Our leader isn't even
John,
coming.
can you be their leader?
Oh, it's counterclockwise, like, if that helps.
Yeah, it's backwards. So.
Oh, it's backwards. So it's 1, 2, 3, 4.
I'm just saying the way the names are. Forgive us.
Okay. This is way harder than it looks. Okay. So John, you are 3. No. Yes.
Yeah.
Yes. Yeah. Jen's 1. Mitchell, you're second.
There's a number.
We got Jen.
And then Timo's. Okay.
What time is our presentation?
What time does it end?
I need to know when the cutoff is.
12:45.
Wait, what? You can't be right.
I like your costume better. That was nice.
Are we overtime already? Sorry? Okay.
Yes. Yes, the answer is yes.
Point for you.
All right, I think the battery's dead, so I'm just going to speak up.
Just talk really loud. With that.
Okay. So we will go 10 minutes, if that's okay, with whoever's organizing the stuff, because we're already over time. Whoever's ahead of 10 minutes will win. All right. You will read, I will tabulate.
All right. All right. So we've got 3 categories here for questions. For first category, we got players. Second category, we have RNA, and third category, we have puzzles. These are going to be questions, and we're going to ask them in the order that you guys pick numbers. And so we'll go with number 1, but you guys get to pick the category. So which category? We got player, RNA, puzzles. RNA? Okay. All right. So the most recent labs have a special binding sequence that folds into a hairpin, commonly called what? Well, that's not fair. You've got the guy who created it. Okay, well, there you go. All right, well, fair enough. We
15 seconds. We require an answer.
No, they just did.
Oh.
Did they get it right?
Did they get it right?
Yes, they got it right.
Okay.
What did they say?
The right answer. They said MS2. All right. No, we just get progressively mediocre. So it's the same thing. Okay, this is more for the fun than it is for the prize, you know. Okay. Now we're not gonna do like Jeopardy where we keep the same person that just got it is gonna keep going because then we'll never be able to get to anybody after we get the board. But so we're just gonna go to the second person. Second
Mitchell's group.
Mitchell. Okay. So which one do you want? Player, RNA, or puzzles? All right. Well, that seems to be the popular choice. Okay. So the molecule most commonly used in switches on EteRNA is called what? But what does it stand for? That was easy. All right, so give him 1 point. John.
So rigor.
All right, here we go, Dan.
What's the actual name of the two?
I don't know. That's the guy who made it.
He knows. Let's go.
All right. Did he say he didn't know either? All right. Okay, who cares? All right, so John, the same choice: player, RNA, puzzle.
Why don't we just do something different and go for players?
Yes. All right. All right. Okay. This is hopefully you guys have been here long enough so you know the answers to these questions. This player created the Special Knowledge series.
Oh, I know that one.
Drake 178.
Perfect. You got the numbers right too. It's 1 point for them. Oh, jeez, you're ahead of me. Okay. And then number 4. Players.
Category, please. I heard RNA.
Okay. This player created the Boost Me series. Yeah, that's it. Hyphema? I don't know. Whatever. Oh, I get 1/2 point. All right, no, we'll give it to him. we'll give it to him. All right.
In the form of a question.
Well, this isn't Jeopardy. This is called JMF and maybe Hoglet. All right. Player RNA puzzles. We're gonna run out of questions. What is the only? I like this one. What is the only pyrimidine, or G and A, / purine, C and G, pair of nucleotides that won't potentially bind if directly across from each other?
Is it the question wrong?
Yeah.
The question is,
That's a point for us.
is it the opposite?
Give them a new question, please.
Okay. We'll give you a new question. RNA. Okay. Here's a good one. You did answer it? Okay. That's it?
All right. Apparently it was correct. Thank you. Okay. Mitchell.
Okay. All right. Mitchell. Player RNA puzzles. Okay, cool. We're on an actual new category this time.
Puzzles. Yeah.
Okay. Janderson Lee. Oh, J. Anderson Lee is known for this creepy crawly series of puzzles.
Oh, come on.
Yeah, that's it. Bug series. Yes. Has anybody lost yet?
Can we like pick a player from the team to answer?
Do you want to do that? Okay. John. Player RNA puzzles. Puzzles. All right. Jay Nickel. Oh, come on. Next one. Okay. Eli Fisker made a series of challenging adjacent stack puzzles with a fungal-like name. Timer's going down.
The leader must submit the answer.
Timer's going down.
Okay, John. What is it?
Oh, 4.
What? All right.
Category, please.
RNA. Okay. RNA has 4 nucleotides, and so does DNA. What nucleotide is found only in RNA? That's it.
All right. You should probably move to the difficult questions so we can
All right, well, then you point them out to me.
Okay.
In fact, you can read them.
Yeah, let's do sudden death.
Sudden death. Between all 4 of you? Oh, why don't we just play the game regularly again? Act like we didn't do it.
Okay.
I think you should just pose a question and then whoever just like answers.
Yeah, that's what I'm gonna. Oh, the whole.
We just give it a buzz.
Okay. JMS. John. Oh, wait. Jennifer. Okay. Your group. Most people level grind in RPGs. I level grind for PCRs. Who said that?
Is it someone
Yeah, you might have to guess. Who would know what a PCR is? Is it 15 seconds?
Like Family Feud, she wants to steal.
Who? No.
It was me. See, it's funny now that you know who said it.
Okay. Maybe a 0 on them, so we know we're moving on to Mitchell. Okay. Who said? Okay. No, not do that.
No, we'll remember. We'll remember.
Okay. Who said? There are a lot of things I know. Everything is not one of them. Who would admit to that?
You again?
Who would admit to that?
Did you guess your own name?
It was Jew.
Oh, unfortunately, he's not here. Explain it. All right. So nothing for you guys.
Okay. John's group? Okay. I just seem quick. I really just travel backwards in time with a solution that took me years to get.
Wise words.
Yeah, I think that's a bird.
You got it.
That one.
Nice.
What else?
In the
Keep board. Okay. Tomo, your chance to tie and move into a playoff, or John takes the king's hat. All right.
15 seconds are almost up.
Sorry. All right, this is a good one. Games don't have to include violence to give people violent thoughts. Is that your answer? No. Eli.
Wow, Eli said.
Yeah.
I didn't even.
Well, no, we've learned a little bit about Eli today. Okay. All right, so I think we have a winner because our time is up.
Or we could do the $5,000 extra question.
Would
Or you don't actually get $5,000.
Or nuclear time.
I was going to say, considering what we're going to get no matter what, so you might as well go for
Actually,
5,000.
you know what?
We have a winner, right?
Right, we do, but what are we going to give these guys?
Well, they can, I don't know. I got, here.
All right.
Here's your prize, everybody. Out of my back pocket. You will be awarded a sticker that you can put on your name tag, so everyone knows how you did at EteRNAcon. The gold is for number 1, and y'all can fight amongst each other who gets the other colors.
We went to golf
I guess the next thing is me and Redspa doing.
Yep.
Okay, so.
Is Red actually in the Hangout?
I do not know. It's yours.
Yeah, okay, is Red actually going to present for it?
Good job. Pass it around.
Tell us like.
I love how one of the questions was that you had said. I think the topic here is stuff I said.
We got to pick the date that's
I saw it.
Yeah, exactly.
Hello?
Hey, where's Bob? You pass, John, you mind
Oh, yeah.
passing these up to this team? Yeah, stick it on themselves.
Yeah, I think it's supposed
That's the only reason I moved.
I'll be in.
Well, there's actually all you can plug in. Okay.
okay.
I'm gonna have to.
Hello?
Thanks.
You don't have like.
It's better.
I think it's better because it's freehand.
Hello.
Do we have any panelists?
Yes, I do. Well, you and JMF.
Hello.
So this next two sessions are going to be about puzzle solving, and so Hog and JMF are going to do dual presentations. And so first, Hog and Red Spa, who is virtual, are going to present, and then it's going to be JMF and Ju. So JMF, please come to the panel.
And Red, do we know that we can hear him?
He was in hand.
Hello?
Is that you? Okay. I just want to confirm that I can hear him.
Yes, I'm here.
Okay, very good. Okay, so we're presenting on single-state puzzle solving. I know that this isn't crucial, absolutely crucial like the lab is to what EteRNA is about, but yes, it does play a major important role, letting people get hooked, letting people understand how the interface works, and besides that, it's fun because puzzles allow people to really engage their mind. Logically, how to attack the puzzle that's in front of them, and not just mindlessly flip, trying to find something that will, that will satisfy the constraints. And Red and I have, we asked Tesla's disciple if it was okay to use this puzzle. He said yes. This is Chaos, and it's a somewhat more difficult puzzle than a lot of them are. And what I want to do is just kind of work through how Red and I attack puzzles. And if I'm going to try to go slow, we're not going to get to the end of it where the puzzle is solved. That's going to take too much time. And so what I really want to do is focus on the concept and theory behind how we get these solved. And I'm going to try to go slow. If anyone has questions during this, that's the better time to ask. If we wait until the end, I'm not going to be able to go back and remember exactly how it was and show it to you and all that. So if you'll please just holler out and stop me, or ask a question, why are you doing this, or what, then I think that will work best. Okay, so generally what I do and what Red does at the beginning, I don't know what he does. I start by trying to find the weakest part, the part of the puzzle that I don't understand very well. Like right now, this part seems kind of intuitive. Like I know that will fold, so I'm not really worried about that part. This might be more difficult. I'm just going to go ahead and put these in the way I would. And what we run into are these unstable areas. And Red, how would you proceed here? Do you go ahead and boost everything, or do you take it to Puzzle Maker and try to isolate a certain shape?
Yes, I think I'll try to export this to Puzzle Maker and increase the length of the stack in the middle, which separates the two very chaotic areas.
In case anyone doesn't know, there is a Beam to Puzzle Maker feature now in the puzzle menu, and it will take this straight to the Puzzle Maker. Ta-da! And sorry. Yes, yes. So the reasoning here, to me, what we have, I'm going to switch to natural mode to see how this is really folding. And there are several areas that are unfolding. Right here, this is slipping, and so I want to eliminate all but one area so I can concentrate on one area to solve. So I'm going to eliminate this issue. How do I highlight a base on this computer? Okay, I don't know. Command. There we go. Okay. So in order to keep that from being a problem, I'm going to make the stack longer because that's more stable. Put some GC pairs in there, and now it's no longer a factor, and I can concentrate on these others. Red, which thing should we try to stabilize first? Maybe this loop?
Yes, this free loop.
Which one?
The free loop.
Three,
the one
okay. That one. Okay. So I'm going to make these longer. So these others are not playing into it anymore, and now we've isolated what's going on here. This is the natural mode, target mode. And I haven't boosted this loop yet, so I'm going to boost it with, everyone's familiar with boosting, I assume. I'm going to put those there. And now I've still got an issue here. When this opens up, this is natural mode. When it opens up here, this is really strong for this shape. So the sequence I have is really promoting this shape to form, whereas if this were an AU pair, even though the energy of this loop is a little bit higher, it's much higher in this loop now. So we've actually gained stability for the target shape.
Can you turn on the
Yes. So just to show that again, we went from 0.2 for this loop to 0.5. That's a difference of 0.7. In natural mode, we went from a difference of 0.7 to 1.9, which is 1.2 difference. So the difference was greater in natural mode, meaning we're making the target shape, we're getting closer to stability there than we are in the misfold. So we're coming closer to stability in this area. The things that factor into making this stable or not are the adjacent, everything that's around this loop. Loose, and everything that touches the closing pair. These things can affect the energy of this loop and this loop. When I open up, I have another issue here. This GC pair is very strong. It could probably be in our best interest to make that an AU. But then we get an issue here. But we come closer here now. Now we're only, if you look up here in the top left corner, we're only 0.1 kcals away from stability. And does anyone have any idea what we can do to solve that? Red, what would you do?
The boost that's closest to AU. Change it to uracil pairs, such as two uracil molecules.
Okay, change that to what?
Uracil.
Uracil, okay. You're talking about here? Okay. Well, let's go with that. This boost, it still boosts the loop, the internal loop. As you can see here, the energy is 1.6. Boosting it with uracils takes it down to 0.9. It's not as low as the GA is, but once again, when we open up to this particular configuration is the multi-loop here does not like this AU pair to be turned this way. It doesn't like it. It prefers this. So this double uracil boost will help close an internal loop that was opening into a multi-loop, it will help that. A lot of the times, if you're really close, you can use that. And in this puzzle, I think you probably have to. Now, we think we have solved that loop, but we have one other issue. In the actual puzzle, there are only 4 pairs here. I mean, there are only 2 pairs, not 4. So when we go back down, I think we will find that we have an issue here, that this stack is not strong enough to hold these 2 loops together. And just curiously, have I lost like most of everybody? Okay, very good. All right. Red, would you agree we need 2 GC pairs here? Because when I look at natural mode, let me get rid of that misfold. Okay. When I look at natural mode now compared to target, the 1.2 kcal difference, I don't know that we can make that up without making this a GC pair.
Yes, we will need 2 GCs. Unfortunately, we will.
Okay. And I'm getting a lot more misfolds that I don't want to try to troubleshoot right now. So I'm changing the shape so that I can focus on this one area down here. All right. So now these 2 are coming together. I don't need this U anymore. I used that earlier to block a misfold, and I didn't say that. Maybe it was, hopefully that was self-evident. Okay, and I'm getting a little closer now, but it's still no good. Right here, if I turn this the other way, I think that will help, because in a multi-loop, a GC on with a dangling end here, if it's oriented this way, it's very strong. If I flip it, it's much weaker. It's quite a bit of a difference, especially if that is not a G. And if I want to raise this energy even more, I would like, see, this is a boost right now, a multi-loop boost. I don't know if everyone knows that, but this is boosting the GC, this G here. If I were to make this a G, the energy of this multi-loop would rise quite a bit. And I can flip this around. That becomes, I'm sorry, a C. I said a G. If I make it a C, it raises the energy of that of this loop quite a bit. And I'm getting a misfold here now, so I'm going to do that to take care of that. Okay, I am getting closer. I'm at equal energy now. As you can see in the target shape and the natural mode. So this is one of those unlucky times when, even though you're right there, it still won't fold. Does anyone have a solution? I just need the slightest little bit of help to close this thing. Maybe a multi-loop boost? Red, which one should we use? See here? Unfortunately, I still have these 2, so I'm going to have to boost over here. I may not need this one. Oh yeah, I do need that one. Let's put that back. Okay. Does anyone know how to boost this multi-loop to close this thing up? Okay, let me tell you. It's a G right here. That gave me, it reduced the multi-loop by 0.1. You can see it's 3.3 right now in the loop. Now it's 3.1. That's enough to close it up. I still have misfolds. I'll get rid of those, and that proves that this combination of pairs down here, this is probably going to be the winning combination. Because if I change these around, I get, that's never going to work. The difference in energy is too high. I could possibly do this, but remember in the actual puzzle, this stack is shorter, and I don't think an AU is going to be able to hold it together. So that is how, that's like the first way I would attack a puzzle. I would look for a weak area like that and logically just go through and figure out, okay, how can I encourage the target shape the most and discourage the opening folds? I mean, the misfolds I try to get rid of. That's why we went to Puzzle Maker. But getting rid of where it unfolds, that's, to me, that's the biggest part of the puzzle. I haven't been watching the time, so I'm not sure how much time we have left.
Well, even.
Do we have time for one more shape in here?
How do you just get back?
Well, the URL is still the same, so I would just copy the URL. Ooh. Yeah, I'm trying to paste. I'm not used to that. No, it's auto-saved, I think. Oh, yeah, copy and paste. Here, down here. Yeah.
It's not the same shape.
Good point. I'm right at the end time. Okay, so just to see the shape again, there was only one pair here. So what I would do next is shorten this down, and now this would be the next area to fix. And you would probably, this is like the common way to fix that, but it's not going to work. And I think the reason why it's not going to work is because Tesla's disciple he's very crafty, he's very clever, he will make you think. And these two G's probably won't work. And so the next area to troubleshoot is that, and you have to figure out, okay, how am I going to make this work? And so that's kind of how I approach puzzles, and I think Red Spa approaches them this way. Red Spa, do you have any comments to add?
Not really.
Neither do I. Are there any like general questions? Yeah.
I noticed that when you boosted that free loop, that you did both the cheat pairs on the same side. I know. I think when I was looking, probably just looked through the boosting guide that brought them together.
Or
one. Instead, why did you choose to do it on the same side? Isn't that not as
You would do it here and here?
Yes.
Isn't
that more effective than doing it on the same side?
Sometimes it is, sometimes it's not. The way I had the AU turned at first was like this. And so the reason I preferred this side is because when this opens up into a multi-loop, if you watch the energy here, when I put it on this side, the energy doesn't change. If I put it on this side, it does. I weakened it a little bit. So.
I thought that was more energy for the loop.
Oh, no. The internal loop, if you watch the energy here, okay, it's 0.5 there. It's the same here. And yeah, you can move these around in any way you want. It's always 0.5. So no, the energy difference for the internal loop, it doesn't matter. And that's what's really nice about Puzzle Maker 2. You can quickly verify that kind of thing. You just click around. It took me like, it takes 4 or 5, however many tries it takes to iterate through and see each possible combination. And from then on, you always know. So yeah, Puzzle Maker. Solving Tesla's disciples puzzle without Puzzle Maker is extremely difficult, and only a few people probably attempt that. But anyway, are there any more questions?
When I first heard that players were going to the Puzzle Maker to isolate design, for some reason I thought they were going to make a minimal element, like
to isolate, recreate
the rest of the nucleotide, as opposed to expand the stem. I was curious if.
Yeah. Well, I used to do that too. I still do it sometimes. If there's a certain shape, I just want to see that and just build it from scratch in Puzzle Maker. But with one like this, and there are multiple areas I know I'm going to have to put in there. Basically, what I'll do is just reverse engineer the whole thing, and I'll lengthen the stacks to keep them out of my way for now. But when I'm ready to tackle those areas, all I have to do is reduce those stacks back down. I don't have to keep rebuilding the puzzle over and over. Yeah, and that's something that's in Drake's guide. It's kind of it's a lengthy guide, and it's kind of difficult to read. But he put that in there. That was kind of his basis for getting a lot of that troubleshooting done. If there are no more questions, because our time is short, thank you.
Oh yeah, somebody just hang that out, but
I'll let you.
I can. Okay. But how does that set up? Dual screen, one with my PowerPoint and one on the actual website, so I can do it live. So you can actually see it.
Okay. Do you have your presentation here, or do you want to pull off from email?
I think I sent it to you.
Yeah. Wait, was it the huge one?
I think that was huge. Mine was, it was, but I don't think it's too much megabytes.
Oh. Yeah, I think this is it.
No, that's the.
Oh, that's it. That's it. Oh, sorry.
I think it was after that. Oh, yeah.
Here it is, right? In Juice,
Juice is a different PowerPoint.
Okay. But he also wants to present.
Well, he's not going to be here virtually either, so I'm going to do this.
Oh, okay.
Sounds good.
So do you want me also to download this then here?
Sure. Yeah. What about that split screen?
Oh yeah, split screen.
Do you think I need to do it? Do you think I need to do it live, or can I just do? Because I've got pictures on it. I just was afraid it would be boring. But I mean, if you think it's alright, I can just do it.
Well, I think we can do it like this, right? And you want to have the actual
website open so I can speak on. I mean, if it's too difficult, it really isn't a big deal.
Yeah, I think. Ooh. I think this way is probably the best way.
Okay.
And this is good. Let's log it. Oh no, Lee, what did you do?
I was not signed in.
I'm kidding, I got it. Okay. Okay. Hi, I'm JMF, as you know from the game that we just played before. Many thanks to Aropi for making the PowerPoint from my Word document that I sent him. It looks really nice, and unfortunately, Drew can't be here, so I will read his PowerPoint for 3-state switches too. And let's get started. So, switches, nature's transformers. Basically, we've got the FMN molecule, which is it's basically a catalyst. It adds energy to structures that would otherwise not form. It's basically taking the secondary structure and letting it form from a puzzle. But without the molecule, it'd be the first structure, right? So switches are kind of cool like that. You can switch them based on like GU pairs. If you got one GU pair that would not fold in reality, you've got the molecule can help that fold work. You've got solving puzzles on screen. Okay, so just like Hog said, basically you can't use this always in lab. In fact, usually it doesn't work in lab, and that's one of my problems. Is I can't do this stuff in lab, but I can do it really, really efficiently just in the challenge puzzles and player puzzles. So basically, I'm just going to tell you how to go about solving a switch in challenge puzzles. All right. Basically, switches with lock bases. This is going to be the first kind of strategy here. So this is the bound state challenge of the puzzle FMN switch 1. So let's search that here. Okay, so, whoops. Don't look at that yet. How do we... Okay, so if we go into state 2, right here, this is the FMN binding site. Okay, it's usually it's in the state that has the molecule binding. So this is going to be the one that's less energy normally than the first state. What we can do here, it actually helps you figure out what bases to pair with it in the first state, the unbound state. So if I look at these bases and then I go to the first state, they're pairing with things that are right now they're not assigned any actual nucleotide but A. And so what you can do is you can figure, well, if I want to use for adenine, the only possible pair is U, right? So what we can do is mark it. If you have a Mac, you can use the command key and then click it, or you can use the control key and click it, I think, on PC. I'm assuming that's true. So let's put use there, keep it marked. Right here, there's two possibilities. The best thing you can do is the highest energy. So the highest energy would be a C. Okay, and we don't know that's for sure what we do. Well, but just let's try and pair everything up first and get it all paired. So we'll do that here too. Reds with the C's, J's with C's, and A's with U's. Ooh, good pair. All right. These right here, they're unpaired. We're not going to worry about them. Okay. All right, let's go to the next state. Now, notice that they're all still marked. We've got unpaired ones now. These you can unmark. Okay. For here, I don't know how exactly you turn off these the yellow blinking stuff, whatever, but just don't worry about that. For here, let's keep on marking highest energy that we can make. Mark these ones, but unmark the ones that you changed last, so that you can keep track of what you're doing. Then you know exactly what you don't have to change anymore. So that's what we got. We go to the next state again, repeat the process until we have until they're all knockdown bases. So we have one more here. I think this is going to be unbound in the end loop. Nope. Let's keep doing that. All right, so here it ended in the very end loop. We can unmark that. Now we would go about a different strategy that I'll tell you about, but I'm not going to finish this puzzle here because I don't have time. I will do another puzzle in a moment that I will finish. But
Dave, are you guaranteed to always at some point stop, or do you ever get stuck in the circle?
oh, no. 3 straight switches is where you get stuck in a circle.
Okay.
But here you pretty much don't. There are problems with that strategy, but I haven't even gotten to that yet. So, all right. So basically, I call that a cascade, and it's basically just pairing things until they become unpaired in another state, and then you can start another strategy process that we're going to pretty soon. All right. It's kind of hard to do 2 things at once. I think I'm way ahead. Okay. Here's the next. The next strategy would be same states or same structures in both states. So for this example, I'm using Drake's FMN switch mod. So let's do that. All right, so here, what you can do here is you can do a PIP mode, which means you can see both states at once. See how I click that window, kind of looking button down here in the bottom left? It actually probably need to do that. Okay. So here, if you look at this, these bases right here, notice in both states, they're the same structure. They don't move. And so what we can do there for now, not necessarily, it doesn't necessarily always work, but for now, to get it out of the way and make sure that it's not mispairing with other parts of the switch, let's just make it the highest energy we can possibly make it. So what I did was I did all CG pairs and 1 G boost. All right. I don't know. I think if you go closer, no, I have to turn that on. All right, so if we
highlight restricted sequence. Go back.
Huh?
Highlight restricted sequence.
Oh, there we go.
Undo. Thank you.
Nice. Okay, thank you. All right, so that's the highest we can do with the energies right there. So that takes care of a potential mispair problem between the whole puzzle when you're actually trying to solve it in pair altogether. And that was the second out of 3 puzzles that I'm going to use as strategy. Now we'll go on to an actual solving an entire switch puzzle. And for that, I'm going to actually use Broad's mod of FMN Aptamer. Thank you, Broad, because he made it really easy. And I wouldn't expect that he would ever do that. So, it was probably an accident. So, let's do that. All right, so first thing we can see here, we've got 2 strategies that you know about now that I just told you about. We can see that the FMN binding site is all locked. So we can use that to our advantage mark them all. And really, you don't have to, but I'm just doing this kind of for your benefit so you can see what I'm talking about. So in the next structure, in the next step, you can see what I'm going to be binding with. We also have same structure part here. This is the same in both structures. Now what I would do first, what strategy I would pick first is I would solve the same structure one first, just so we can get that completely out of the way. So let's do that. Highest energy, in this case, we've got across GC, and then all the rest of them are adjacent. And that keeps it 3.4 for one quad, and then the rest are 3.3. All right, so that's taken care of. Now we can go back to the other strategy that I've used, and we can use that. So I would put all the highest energies into these. Now remember what I said, the locked pairs that aren't, the locked bases that aren't paired with anything, just don't worry about them right now. We'll worry about them later. All right, so let's put this back into this mode. All right, so let's get to it. We've got and pairs with blue, yellow, yellow. Skip that. Don't even mark it. And notice here you could potentially put a G there and make it better, because now it's -1. But we don't know if we can actually do that because it might mess up the entire second structure. So let's not even worry about that. All right, so next place we've got 2 unbound, 3 unbound. And go to the next one. Got 1 unbound. Now here, you would think that it would maybe bind with that if you weren't as advanced as I am. but in reality, when you have a tetra loop, this would not be able to bind. It would be too much energy that you would need in order to keep it down. So we won't worry about that. That's fine there. You can see the yellow here stops, so we won't worry about that. Let's keep going. Almost done here. And notice these two were marked originally, and I unmarked them, but that's good that they're not permitting and purine that could potentially form together. One more. All right, here. So here, luckily it was the last one that I changed. We have a problem with the other base that's next to it. This is where the purine 23, what are you talking about? All right, well, anyway, with, here we go, okay. So you've got all the cascades over. With this one, I want to now actually keep it from pairing with this one, because if you look at the natural state, it wants to pair, okay? So in order to do that, I have to make it mismatch, and you and you are both, tell me if I'm wrong, purines, purines, one of those. Anyway, and purines can't bind together, and purines can't bind together. So let's make it the lowest, the one that would cause the lowest energy. It wouldn't mispair with an A, rather than the C mispairing with G's and G's mispairing with C's. So we change that to blue. Now we follow that cascade, and so that would be right here. Right, okay. All right, so you've got, next one would be So U across from A. Okay, so now I would go from the top on down, because now we're at a point where everything's paired that you can tell has to be there, because they formed from the line, except for this one. That's weird. If someone that I didn't know what you were saying. All right, so that's good. All right, so now I would work from the top, okay, and then go down for the pairs that haven't been paired yet. So for here, this is I would look at the entire stack as a whole. It's only 2 pairs long, so I want to make it a high energy while keeping this pair here because it needs to be there. So the highest energy I can do is this orientation of GC. Okay. All right. Sorry. This orientation, -2.4. Okay. I'd highlight both of these, and I'd follow the cascade again like I usually do. Okay. All right. That's good there. That's fine. And that's good there. All right. So I would do that. Next thing I would do. All right, here. So now we're on to this part where there's a stack of 5. For the stack of 5, I want to keep it as low energy as possible right now, just because I don't want it to mispair with anything.
Which state are you? How can you stay in this state?
For this state right now, usually I just stay in whatever state is state 1.
Does it matter?
For right now, it doesn't. It'll matter once I'm done pairing this. If there's still pairs left over that I need to pair, I will go to state 2. All right. So now I like to do AU alternating. So I'll do that all the way down to the bottom here, which we'll get to a point where I'll have to explain another strategy. But until then, let's have some awkward silence. Okay. Sorry. This is fun, huh? You can't really pay attention to the outside world with this. And then one more here. Okay, so we're going to kind of problem here. Okay, so notice, in this loop, you've got potential mispairs that could happen. This yellow, this adenine right here can potentially pair with this uracil right here. And you can't really change that no matter what you do. Even if you change the orientation, the blue, if you changed to here, there would be a yellow here due to the cascade pairing like this. So what I do is try and make the more favorable energy more favorable than a mispair. And the way to do that is usually to go by making the most stable or the least energy using GC pairs. So I know that GC pairs you can substitute pyrimidine and purine. So you can substitute uracil with cytosine and adenine with guanine. So notice that they still pair, they're still fine in most states. All right, and notice that also because there are no bases in between these potential stacks, there's no difference even with the orientation to the actual energy of the loop. But if there was a pair in between them, the orientation would be red to the left and green, well, red to the least numbered nucleotide in the sequence, and then green to the highest number. So we'll keep it this way for now. Now we have 2 more pairs left in this actual thing to pair up with each other. So let's continue doing the alternating AU pattern. All right. So now we've got everything pretty much paired. Okay. So now we've still got some stuff that's not pairing, but everything everything, even in state 2, is paired, right? So now we just got to stabilize the thing. So if you actually press on the mini-maps, since we're in state 1, we'll press the state 1 mini-map, it'll highlight what's not really binding right, okay? The problems. So what you can do is you can try adding stronger pairs and replacing low energy permitting purine pairs with high energy, which is GC. So, but you keep the orientation of which permitting is where and which purine is where. And so what I did is I started here. I started with the one down here. If you can start with other ones, and in fact this works, but let's just go with this because it'll stay consistent with my guide. All right, so notice, the state 1 is finished. Everything's bound and it's stable. But state 2 is still not working in these areas. So now we know that the one that I just changed, it made a GU pair right here. Okay? Since it's not binding in that area, we know that's probably what's making it not bind, or helping it not bind anyway. So we want to make that stronger. So let's change that to a C. And look, it didn't even affect the first state. So that's good. So we can take away those, or we can unmark those bases. Now what I would do is the end game. I would basically just do permitting purine substitutions, and as long as they don't, affect the first state, I keep them in until this thing solves. And so what I did was I did that for 5 pairs that it didn't affect the first state, but it made the second state stronger. And let's see what happens. So we've got I do that? That's not supposed to be there. No, that's supposed to be there. That's why. There we go. Okay. All right, so now both states are stable. However, these stupid constraints keep us from the puzzle being solved. So the only thing that happens that we need to change here is in the, it just so happens to be perfect, Roy, thank you, is that in the same structure part of the puzzle, there's 6 in a row, right? Let's just change one thing and see what happens. So that solves the puzzle. All right. And that's the end of my presentation. All right. Well, now we go into Jews. Pablo? You want to hold off for the questions?
Are you going to show us 3 state now too?
Yeah, I'm just going to go.
We are sort of out of time, but.
Do you want to just pass it out and then?
I have some copies of the Jews presentation because it's too long. You're going to present just.
It was going to be a 2-minute video that I was going to show.
Yeah, so it's a 2-minute video, so it's fine. And then.
And I really want to do it because she was really looking forward to it. So. All right. So, do you know how to pull up?
Yeah, I'll put it. Okay. Wait, there's a video in the PowerPoint?
Yeah, you just press it twice and it starts playing.
Okay. Where is this thing?
Yeah.
Here. And we can just show it from there. I'm fine with that.
Okay. So where is the video?
I'll get to the video, but I gotta go through some stuff here. All right, so this is Nando's.
Should I distribute the handout or?
Yeah, you can do that now. This is 0 to Q or whatever. It's Nando's bot spelled it, so apparently it's not good at English. All right, so he wanted to do a triple switch walkthrough. Unfortunately, he couldn't be here, virtual or actually here. So he made about 9 slides, I think. Good afternoon, friends. That's what he says all the time when he when he enters the Eternal website. Big thanks. Sorry?
House flips.
There you go. A big thanks to Eli Fisker for asking me, these are his words, not mine, for asking me to write this guide and for his years of support, encouragement, and kindness. Further thanks to Elnando888 for permission to use this puzzle as a walkthrough and for noting that there was little he could do to stop me. Thanks for the switch. Final thanks to the entire Eternal community, RNA aside, that's also my words. What a wonderful, knowledgeable, funny, tolerant, and supportive group of players. Wake up, Roy. Disclaimer, the JIRT-Q method will work for many, but not all triple switch puzzles. Some puzzles are designed to... Just gave you away the answer. Some puzzles are designed specifically for this approach, like Weiwan or whatever. The good news is that using this method can be a pretty fast way to find out whether or not it will work. All right, so I'm going to kind of skip this since we're kind of out of time, but it basically, he'll put up a guide on the actual website for the entire walkthrough. But here's just the video walkthrough of him going through it pretty fast. It's about 2 minutes. That score. All right. Well, thank you guys for listening. Oh, here we go. Eternal, congratulations. Thank you for taking the time to walk through this abridged version. All right. The rest of it is actually on the papers that he gave you, but I think I told you, did I tell you he was going to put the guide up on the website?
Yeah.
Okay.
Everything.
Everything's gonna be.
Everything that's presented here will be available on the site.
Right.
Okay.
Yeah. There's also YouTube videos. Thanks.
Mm-hmm. Can I plug it? Yes. Hello? A little higher? Okay, can everybody hear me? Great. Am I being amplified? Sounds like I am. All right, well, I want to thank the organizers for the wonderful opportunity to speak at what this is a historical meeting, I think. So I want to introduce myself. I'm a bit of an outsider to the Eterna world, but I will be talking about scaling Eterna labs to ideally solve biology. I think that's a big goal, but I say we dream big. And so let me quick introduce myself. My name is Will Greenleaf. I'm an assistant professor in the genetics department here at Stanford. I guess in my lab we've been doing the RNA array experiments with EteRNAcon, and then after I give this talk, we'll go to my lab and have a tour of the instruments and things like that. So I'm going to be talking about sort of the infrastructure behind the high-throughput RNA array and things like that. So first I want to introduce sort of why I'm interested in the problem, I guess. There's this sort of grand challenge question, right, in I guess, biology or biophysics or structural biology, this question of how information in DNA sequence here, gets converted into actual physical biomolecules, molecular structures like this RNA hairpin here, and then how these RNA hairpins actually do things, or how these molecules themselves do things. For example, this RNA hairpin is able to bind this MS2 protein, right? So this is a big question of how we might be able to understand how changes in DNA sequence, be they changes that occur between different individuals in their genome, how these variations might couple into the structure and function of biomolecules. And so DNA is this combinatorial polymer, and of course, as is RNA as it gets transcribed from DNA. So I think really, in my view, what we really need are these incredibly high throughput methods for characterizing this coupling between sequence, structure, and function. And if we can do that, we can also sort of invert it, right? We might be able to say, okay, we have a function that we're really interested in. We want RNA to do something for us, sense something. And so now we have a function that we're interested in. We might then determine what structure it might form, and then we would generate a sequence to actually do that job. And again, to test these sorts of design problems too, what we really need, I think, is these high throughput methods for characterizing large numbers of these hypotheses. Now, has anyone seen this graph before? This is from, yeah, okay. A few people are shaking their heads. Among the people I often talk to, this is maybe one of the more trite slides imaginable. But honestly, it's a very profound observation that I think I want to dwell on a little bit. So this is graphing the cost of sequencing DNA per genome, a human genome, as a function of time. So a human genome is about 3 billion bases of DNA.
Okay, so the Human Genome Project was completed, around here. The integrated cost was about, say, $2 billion to sequence the first genome. And as we go along, this is a log scale in cost. You can see this dramatic reduction. And actually today, this line goes to about here, $1,000. So we've had a 1, 2, 3, 4, 5, and honestly, there was up here, maybe 6 order of magnitude improvement in the cost of sequencing DNA over 12 years. And I claim this is unprecedented in the history of technology development of any technology ever. Does anybody, anybody? So I gave this talk to like some physicists, and they said, actually, the transparency of glass improved about like this. I was like, well, that's lame. What does it matter, right? But actually, it's not lame. It's not lame at all. That's what allowed fiber optics and the information revolution. Okay, so this is the biological information revolution, right? This incredible improvement in the ability to determine the sequence of DNA. And really what we're doing, or what we're trying to do, is hijacking the engine of this incredible growth to then couple it to try and answer these questions of how DNA sequence actually affects structure and function of biomolecules, and then also test proposals for functional biomolecules based on the sequence. Okay, and so how are we going to do that? Well, remember, we want to make lots and lots of measurements. We want to make lots of hypotheses. We want to test them all. There's lots of different scales of biochemical functional assays. Obviously, one can start to have a bunch of tubes in a lab, and then unfortunately, you need a lot of grad students, and grad students, right? Sorry, wrong crowd. Okay. So maybe you could do hundreds of different tubes. You can do 96 well plates. You can do 384 well plates. You can get to microfluidics. Maybe do 1,000 things on a microfluidic instrument. You can get to microarrays. Maybe do a couple thousand things. Obviously, there's this limit of miniaturization of these assays at the single molecule level, but single molecules are a giant pain in the behind, and I speak from experience. It turns out the sequencer itself, this Illumina sequencing platform, lies at a wonderful place in this continuum of miniaturization right here, where you have an array of different DNA sequences. Each one of these clusters is about 1,000 molecules, and each one of the clusters also started from a single molecule and was clonally expanded to about 1 micron worth of space. And then you have 1,000 molecules in each one. That means in something I can hold in my hand, I can have approximately 1 billion different experiments. Okay? And this is what has driven the ability to sequence genomes. Basically, this platform is used to assay whether or not a DNA polymerase can incorporate a fluorescent nucleotide at each one of these clusters. Each one of these clusters has a different sequence associated with it. And then there's this fluorescence imaging that gets done to read off the colors of all the different clusters, and that's how people can sequence a genome for $1,000 these days. And I want to go a little bit deeper into the molecular biology underlying the technology, because it's really what's driving our ability to do these high throughput labs. So the way the sequencer itself works, the way we make all of these different clusters that are all independent measurements, is that first we start with a DNA molecule. And it has a special structure to it. It has a region that looks like a D and a C, and this is common to all the molecules in the library. So this is just one example of the molecules in the library that we put on a chip. There's this V region, which is the variable region, and then there's a region which we're going to use to read. And it actually goes onto a flow cell that has all of these primers on it. So these primers are pieces of DNA that are complementary to either the C or the D region. Okay, so that means because they're complementary, that is, they make ATGC base pairs. Then this guy's going to land and pair up, right? And the way this is oriented, it turns out that if you add a DNA polymerase to this flow cell, it's going to extend and copy this fragment. Okay, and so now I can copy that fragment onto the surface, and I can flow out that guy because I made a copy of him. And now he's on the surface. So I have a single molecule of DNA on the surface. And now I'm going to do what's called bridge PCR. So who knows about PCR? All right, half and half. Okay, so the idea here is that this portion of this molecule, remember, is complementary to, okay, we got rid of him. This portion of the molecule is complementary to this primer on the surface, so it's going to bend over and anneal to there. And now if I add DNA polymerase, the polymerase will come over here and copy down to here. And so now I've made 2 molecules. Sweet. So, but if I do it again, guess what? How many molecules? Ideally 4. And so now I'm amplifying these molecules, and they're all identical copies, or reverse complementary copies anyway, of the same molecule that landed there. So I'm making a little colony, and so I do this a few times until I have lots of copies. And again, that's what a cluster is. It's just a region where a single molecule landed, and I've amplified it to about 500 copies right on the chip. And again, that's what a cluster is. Okay, so then what I can do is cleave off one of these strands, add a sequencing primer, and then use this fluorescence-based sequencing where we add different colored nucleotides and see which ones they add to determine what the sequence of all of these molecules is in that specific cluster. Okay, and I did that to all the clusters on the chip. Okay, so now I've sequenced my chip. I've got the sequences of, like, let's say 50 million different clusters. And now I have a DNA array that I know the sequences of all the different clusters. Now what we're going to do is convert it into an RNA array. Okay? So the way we do that is, what we did was when we sequenced it, we had a structure of the library that actually also looked like this. It had a special region where an RNA polymerase can initiate, a region that's going to stall the polymerase, and this variable region where we can program in any RNA that we want to get generated. And then this other stall region where the polymerase is going to choke. So it turns out what we do is, again, we make these clusters, we sequence them, we know the sequence of this variable region for each of the clusters, then we make double-stranded DNA, and we have this special roadblock at the end. Then we initiate this RNA polymerase. This is an enzyme that's able to read DNA and copy it into RNA. This happens all the time, obviously, in the cells in your body. This is actually E. coli's version of this polymerase, where it starts here and makes this RNA until it hits this stall at the end. And now I've tethered the single-stranded RNA to the DNA mother template. And now I can add, for example, MS2 or any other anything else I want to do to probe this RNA. And of course, this RNA is one specific RNA that's home in one cluster on the chip. But of course, there's hundreds of millions of different clusters. Okay, so simple case study, and you guys are maybe familiar with this MS2. This MS2 protein is a protein that likes to bind this canonical stem loop sequence here. It's one of the best studied RNA binding proteins of all time. Here's what it looks like when it's in contact with RNA. And so in order to understand the affinity for MS2 as a function of sequence space, what we did was we engineered a library that looks like this. And in this variable region, we programmed in a bunch of different MS2 stem loop structures. So we started with the canonical sequence that it likes to bind, and we made every possible single mutant and double mutant and triple mutant and many higher order mutants as well, and asked how well that MS2 protein likes to bind to the different structures on this array. And this is what the experiment actually looks like. So I'm going to explain real quickly what you're about to see in the movie. So what this is it's about 1% of one lane of an experiment. So each one of these little dots is a different cluster that has a different RNA sequence generated off of it. And we're going to look specifically at this cluster. A little quantification will pop up here, and you'll see a binding curve for that cluster specifically. But what's going to happen is this is all the RNAs that we're lighting up. Then we're going to switch to a channel where we're looking at the MS2 binding, the fluorescence of the MS2 actually landing on these different clusters of RNA. And we'll flow in higher and higher concentrations of MS2 and watch which sequences like to bind early and which sequences like to bind late. That is to say, which sequences bind tightly and which sequences are less tight at binding. And then we'll also flow off the MS2 and watch it go away. Okay, so here's what it looks like. It'll go dark when we switch to the MS2. Oops, that was really fast. Okay. So we're switching to the MS2. Here's higher and higher concentrations of MS2. Some of those clusters are binding, and now other clusters are lighting up at higher concentrations. And then we're flowing out all the MS2 and watching the decay of fluorescence as the MS2 floats away into solution. Okay, so from these data, we get these binding curves that look like this. So as we go higher and higher in MS2 concentration, in this specific cluster, we see that the fluorescence starts coming up and then saturates as all the RNA on this cluster is bound. And that's this cluster specifically. And if we have a different mutant, this is the -5U mutant, it binds less tightly, so it takes more MS2 to bind it. And then this green mutant's even worse. And then finally, this G mutant is a disaster. We can't get it to go on at all. Just a single point mutant in the loop, it turns out. So we can see for each one of these clusters, we can get a reported delta G for the binding to that RNA sequence. And I don't have to go through this too much, but the measurements that we see on the array agree with literature values very well. So we're pretty confident in the measurements we take. We also take multiple measurements for each molecular species so that we can get statistics and be pretty sure what we're looking at. So, for example, then we can say, okay, what does the mutational landscape of this simple hairpin structure, how does that landscape couple into the affinity to the MS2 protein? So here is the binding energies for all double mutants of this structure. And the single mutants are across this diagonal. And if you're a red point, that means you're binding very, very tightly, like the wild type. And if you're a blue point, you're binding like crap. And the protein doesn't recognize you as something it should bind at all. Okay? And you can see some interesting structure here. These high tight binders are the compensating mutants, where instead of having an AU here, you have a UA, for example. Or instead of a UA here, you have a GC. So the protein cares a lot about the secondary structure of this RNA. And I should also mention we have tons of data, and we can look at triple mutants, for example, and make maps of the triple mutants. But we can also map the relative energies associated with binding associated with the primary sequence here. So if I make mutations to these specific bases themselves, but maintain the secondary structure, versus breaking the secondary structure. So this is the sensitivity to that MS2 of secondary structure versus primary sequence, and we can partition all of that out using these sorts. Okay, so that's just a quick demonstration of the sorts of questions we can ask in a quantitative manner using the high-throughput array, and obviously we can also, and Johan will be talking more about how we've been assaying designs and labs that are associated with EteRNA. But I just want to talk about the instrument itself and how we actually do these experiments going forward, including for EteRNA. It turns out pirating sequencing instruments is cheap and potentially easy. The GA2, this is a sequencing instrument generated by, made by Illumina. Maybe 6 or 7 years ago, it was the absolute state of the art and cost approximately $600,000. Now they are giant paperweights, and you can get them for basically $0, plus or minus $1,000, something like that. So we have a ton of these things, and they have parts. If you open them up, it looks a lot like it was built by a grad student. No offense to grad students in the audience. It's great. There are like structural cable ties in there, and you can cut everything apart and repurpose it to your ends. And we also have this sequencer, which you'll see, a MySeq instrument, which is a very efficient, simple, fast turnaround, relatively low-cost sequencer. So we're able to do the sequencing on these MySeq chips, and then take the chip and use the guts of this instrument to do our quantitative fluorescence measurements associated with binding and the assay itself of the function of the RNAs that have been generated. And we've been using these custom-built, pirated imaging stations, which you'll see. And they have custom hardware in that lab control. All right, so we also have our own high-throughput fluorescence GUI and software. We can drive around and look at all of these clusters and control temperature and laser intensity and things like that. We can also clone these things because we have all the hardware and we have all the software. We can actually generate a large number of these imaging stations, and we have two and a half that are currently operational. So let's see, how much time I'm almost out of time. Sorry. Okay. So I'm going to run really quickly through some of the things that we can do on the academic side, and then I want to just give a really broad overview of, I think, how much farther we could go with the throughput. And what that might mean for the future of EteRNA. So some of the things we're working on in the lab are trying to understand the determinants of tertiary structure using sort of a hydrogen atom of tertiary structure formation, which I'll talk about really briefly. We've been exploring the molecular determinants of function, especially interactions in 3 dimensions, using a complex RNA machine that's able to cleave itself. We've also been looking at DNA-protein interactions in extremely high throughput, but I'm not going to discuss that. So one of the things we've been looking at, and again, this may couple into sort of a 3D vision of what RNA can do, is looking at the determinants of tertiary structures. So this is a model system for tertiary interactions called tecto-RNAs, and these 2 heterodimeric simple loop structures can have loop interactions at these 2 positions, and this can bind actually quite tightly. So we've abstracted this in secondary structure to look like this. And so what we can do is make enormous number of programmed variants of this structure on the chip and determine how it changes the binding affinity of this partner in solution. So really simply, for example, so how does this work? Well, we engineer our library. We generate the RNA. It folds into the binding partner on the chip, and then we have a flow piece that's labeled in solution. And you can see again here all our clusters, and we can increase the concentration over time and measure binding affinities just like for a protein. So for example, here what we have are different lengths of the piece on the surface, 8 base pairs, 9 base pairs, 10 base pairs, 11, and 12. And you can see as we walk up the length of this simple hairpin, there's some optimal length that the flow piece likes to bind. And then as we get even longer, it doesn't like to bind anymore. We can build sort of an energy diagram of where this tertiary interaction likes to be. We can look at helix sequence. So if we change the sequences of the helix but keep the length the same, does that change the energy of interacting with this flow piece? And it turns out there's actually relatively large, surprisingly large effects across sequence space, and we're working with Riju to understand what that might mean. We can also make bulges. So we can make 1 by 0 bulge, 2 by 0, 3 by 0, 0 by 1, 0 by 2, 0 by 3, 1 by 1, 2 by 2, 2 by 3, and we've done every single possible combination of these different bulges and asked how it affects the binding of the partner. We've also been looking at this complicated RNA. It's about 500 base pairs long, called the tetrahymenorybozyme. It has a very large number of really interesting structural motifs, obviously base paired helices, helix junction, helix elements, hairpins, single-stranded regions, receptors, loop-loop interactions, all sorts of motifs. And we can knock each one of these components out and ask how the molecular function of this ribozyme, which is actually to cleave itself, how that is affected here. And so this is just an example of what this looks like on the chip. So basically what we have is this ribozyme is able to cleave RNA right here, and if it does that, this label flows away. So the decay of fluorescence is a measure of how well the structure is actually functioning. And so as we go along, some of those structures are cleaving quite well, some of them aren't, different timescales, and a bunch of effects from different means. Okay, so let's talk about future outlook, perhaps, for massive scaling of these fluorescence functional assays. So the current chip allows measurements on the order of 1 million structures, allowing 20 measurements for each molecular variant across maybe 50,000 molecular variants, and maybe Johan has better numbers on this. This is what my memory served. So 50,000 perhaps is the kind of the level we might be able to get to in the relatively near term. But there are definitely, there's good prospects in the relatively near term, maybe the multi-year term, to maybe dramatically expand this. So there's existing high throughput chips, and improvements in analysis may allow up to 200 million measurements across 10 million molecular variants, with 20 measurements per molecular variant. Also, improvements in DNA synthesis fidelity and construction may lead to the ability to synthesize high fidelity programmed sequences on the order of 500 base pairs. And of course, the number of different sequences possible across 500 base pairs of RNA is something like 10 to the 100. So that's many, 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 many more possible structures than the number of atoms in the universe, right? So that's lots of dimensionality to play with. So this is potentially a 10x scaling in measurement, and 100x scaling in measurements and 10x scaling in length. And at this scaling, we think we can, the sequencing cost, at least per assay, for each molecular variant would be on the order of 0.02 cents. So that's cheap. So what are my take-home messages before I get off the stage? Well, we're at the brink of allowing nearly anyone on the Earth, I would say, to carry out these functional experiments of DNA or RNA sequences for relatively nominal cost per experiment. This really opens the door, I think, to the possibility of a disruptive change in how science and biomedicine might get done. This idea of crowdsourcing science, which everyone here is very intimately familiar with. And so I sort of wanted to throw out, obviously, the question: how might we be able to maximally leverage this platform for good? Would be nice. And I'll leave it there, and then of course introduce Johan, who's a joint postdoc between myself and Riju, who's been doing all the incredibly hard work to get the data from these experiments. And maybe 1 or 2 minutes for questions. That'd be great. Thanks. Oh, also, these are the people who actually did the work and stuff. So that's important. Maybe 1 question, or anybody? Yeah.
So I would do a professional disclaimer. I work for IBM in big data and analytics and performance management.
Okay.
So has your lab looked at putting together specific either predictives or predictive engines or sort of high-powered data analytic tools to go with the amount of data you're generating in your experiment?
Yes. Well, so it depends on I guess exactly what you mean by analysis. There's multiple levels. There's a primary analysis pipeline that involves quantifying the fluorescence from the images and doing fits to the clusters and then voting, which sort of coming up with bootstrap errors on the means and things like that. So that all of that sort of pipeline is more or less in place. Then there's higher order inferences about sort of modeling the data, trying to understand what it tells you about science or the energetics of interactions, or there's a million questions we might want to ask from the data set. And I think we're just starting to go down those paths of developing tools for those sorts of inferences. I think there's also a lot to be said with respect to painting on structures data, so that that there's sort of an intermediate between machine learnable and human learnable, so that people can sort of have a better bandwidth for interpreting the massive scale of sort of data that exists. And these are hard problems, and I think we've only started to approach them. And obviously, we would also love to get feedback from the EteRNA community with respect to how to generate these tools that are most useful for people who are actually doing the design. So that's a long, rambling answer, but so there's a lot to be done. This is the short answer. Yeah.
How do you associate the specific sequence with the location on the jet?
Yeah, that's a great question. So the sequencer provides information about the center of the cluster, where the center of the cluster was in the sequencing run. And then when we take images, we have a cross-correlation algorithm that takes all of the cluster centers that were predicted and cross-correlates it with the centers we observed, and then aligns everybody up. Then spatially, we know where
So nothing is done manually. You don't have to like pick this center and say, okay, sequence it. Pick this
No. So we can't do anything manually on the scale of tens of billions, or at least Johan won't work hard enough. Okay, thank you.
Okay, thanks, Will, for the introduction with a lot of info. I'll try to just touch a little bit of where we want to take this technology, and because a lot of players probably noticed that there are a lot of changes happening in EteRNA, and I just want to give a kind of a sneak peek of what we want to do. So we already touched upon the idea of turning what we do in EteRNA to actually creating biomedical innovations, or so it could be drugs or it could be diagnostics, and it sounds kind of lofty, and it definitely sounds much more lofty than this explanation I found on Scientific American, where it says EteRNA is a game that lets citizen scientists participate in creating a large-scale library of synthetic RNA designs. That one sounds really boring, and I don't think anyone agrees that that's what we're actually doing.
So I was going to try to just show what we really want to do. I do think, though, that this one, it has a lot of the characteristics, or sort of the words of what we want to do. So, for example, it's large scale, as Will just showed in his presentation, and we are doing synthetic RNA designs. But I would really say that we're not creating a library. We're creating methods and strategies, and we're being creative in a way that I think sets Eterna apart from many of these other crowdsourcing projects that are going on, where it's often scientists ask the players, or not the players, but the citizen scientists go out and collect dirt samples or swab their cheeks or something like that. In this case, it's actually the inverse, where we ask the players to do the science, and I think that's what really makes Eterna exciting. And even then, if you tell people that, oh, we're going to design drugs online with players, it sounds. I can see that some people would be skeptical, and if you tell me, I would maybe be there too. But then I realized that I've actually seen this happen in real life. So it turned out that just a few years ago, my wife got ill. And she tried, all the standard therapies for, in this case, an autoimmune disease, and nothing worked. But then somehow she did research online. Her parents found some herb from China that they got via Japan or something like that, and it worked. So she got cured from her autoimmune disease taking this drug. But she didn't stop there. So that's how I think a lot of people try to take their health in their own hands, for example, and there are a lot of people doing research on their own. But what she did, she actually took this idea, and she started reading more, and she pitched this to a drug development program here at Stanford, and they liked the idea, and now we have even taken it from just trying it at home to actually setting up a clinical trial where we're giving this to patients here at Stanford, hoping to develop a new drug. So it shows that a random person can actually do this and can actually come up with ideas to make new cures. The problem, of course, is that players aren't at Stanford, right? They're at home, they have good ideas, but maybe there's this connection between taking it from an idea, from a good design, and making it right. So that's what we hope to facilitate with Eterna, to take all the great ideas from the players and collaborating with labs at Stanford or maybe with companies to bring some of these ideas to fruition, to make something tangible that we can actually use in the clinic. And just a warning sign though, my wife ended up quitting her music program and now is doing a PhD anyway in biomedical science. So watch out, you might get hooked to it. So with that, I just want to touch briefly on what we would like to do with these RNA designs, and also what we've done so far, and finally what we think we want to do. So I think I've shown this slide a couple of times before on some online presentations. But the idea here is that there's already RNA molecule or therapies that have been approved by the FDA that you can use, and a lot more in clinical trials going on. So up here you see, for example, a molecule that cleaves a small RNA molecule in your cells. So you introduce it in the cell, it cleaves an RNA molecule that's too abundant in the cell, and it will cure some disease. To the right is the one that's actually approved. It helps your macular degeneration. In this case, that one was superseded by a genetic drug, Avastin. So it's not really used much, but it shows that it's possible to use RNA molecules for drug treatment. The problem with all of these, and which is common to many drug overall, is that this sort of lock and key. It's like one drug for one single target, and you want to tweak it a little bit by increasing the efficiency of a protein, or you want to just knock it out and block all of the proteins that signal some disease, for example. But what is really cool with RNA, and that sets it apart, is that it's combinatorial, it can switch, it can do very interesting things. So we want to go from a drug that's just like a tool that you sort of throw in the machinery and hope that it messes it up or not, to something that's much, much smarter, something that can sense, maybe sense many different things, and then act on molecules. Maybe just do it in certain cells or in certain diseases and so on. And I think you all agree that this could work. And here I just have one example that I also showed before what I mean by this, by having a smart drug, sort of smart bomb instead of just a tool. So here is one example where we could have an RNA molecule that has an internal ribosome entry site. So the ribosome can bind to this RNA molecule right at this site and then start making a protein. So in this case, we're going to make a sensor in the cell. So I just, for example, put this GFP message, which means that the molecule will create a fluorescent GFP molecule if the ribosome can bind here. Okay, so that's a sensor. The ribosome binds, it creates it. But to make it smart, you don't want it to express the GFP everywhere. It would turn you green, like a green pig you might have seen. So what you would do is you will want it to be off at all times, unless, for example, you have a microRNA in the cell. So when the microRNA binds, you get the GFP message. So that's a simple sensor. Now, we can make this even smarter by adding an aptamer, for example, similar to the FMN aptamer that we've been working with all the time with the switches, where, again, the thing is off, even if the microRNA is there, unless you add some small molecule that turns it on, so an exogenous control that you can drink a small molecule. In this case, I chose aspartame, for example, in your Diet Coke that everyone has on their desk. So in this case, you have something you can control yourself, and it also reacts to your cell. So that's how you can start building complexity by doing riboswitches and make more interesting molecules that might be able to address diseases that you couldn't do with just a simple small molecule drug. And so just to show how this would be laid out on a sort of a logical table. In this case, we have an AND gate, so you get a response only when both inputs are present. Otherwise, it's off. So this is a simple truth table for a two-input switch. Now, it quickly goes very complex if you add a number of inputs. So here's a truth table for a 4-input switch. And this one actually only has one output. This would be really hard to design, but we think that it's something to strive against, or towards, because we've seen already that we see improvements all the time, from static structures to also the switches. So we don't see that there should be a specific limit to how far we try to push this. And just as a sort of a grand thing to aspire to is this Feynman grand prize that Reedy has talked about before, where the goal is to take 2 8-bit inputs and get a 1 8-bit output, which is the addition of those 2 inputs. So you can see that that gets very, very complicated. And this has to be done in a volume that's smaller than 50 nanometers on each side. So that suggests that maybe RNA is actually the ideal way to do this. It's not easy, but I think we might get there if we try hard. So this is the grand prize. That's sort of a lofty goal for fundamental science on how can we understand RNA folding and how can we use it. Now, the reason I think I get excited about working in biomedical science is, of course, the idea that it's connected somehow to our health. And I think everyone here agrees that it adds this extra excitement on top of just puzzle solving, which is very fascinating. I think all of us kind of like to geek out and just figure out exactly how to make intricate puzzles. But the connection to health really, really helps. So that's why we want to not only make adders that work in the test tube, but make drugs. So what we've done so far is to, of course, start these new switch puzzles that make use of the array that we presented. So this one you should all be familiar with if you've done any puzzles the last half a year or so. We started with something that was relatively simple, and we chose to use the MS2 because we know how it works, and we know that we can use it on the array from the previous paper. And the FMN has also been used in EteRNA very much, and successfully with the old type of puzzles. So we thought we combine the two, we combine the FMN aptamer with the MS2 readout, and see if we can detect the switching that way. So this is what we showed you. We did exactly the same way as in the previous paper, where now this variable molecule here is your designs that bind the MS2 hairpin. And I also have a video, I put it in 2 colors, but it's the same idea. See if it comes in. So here, if you increase the amount of MS2, you see that some clusters start binding, but not others. And at the end of it, you also have some that don't bind at all, which is the off switches. So the switches that turn off. So this totally works, which was very cool, I thought at the time. So right now, what we have been doing lately is to use both FMN as a binder and also microRNAs as sort of a second switch. And because we have them all on the same chip, you get the information for all three of them. So you might be familiar with these kind of plots where here, when the switch is on, you see you get binding at the very low MS2 concentrations. And then if you have a good switch, like this one by Eli, whose name is down there, you get this big shift in the parent KD that you see. And so if you sit at this concentration, you see you go from almost full activity to almost nothing. So that's a great switch. So it shows that we can actually do this in practice. And there's been some talk about the number of clusters you need to get a good accurate measurement. And I think that the number 10 or even higher that was mentioned earlier this morning by Lars was probably a minimum number. You will see that there's a big variability in sort of the spread of this distribution. And if you only have one or two clusters, you might end up here or here just by random chance. And it might be that some of the big outliers is simply due to that. And one way to think about it, I kind of like this plot, is to plot the KD in the on state, so the green curve in this case, versus the KD in the off state. So what you want is something that's very low when it's on and very high when it's off. So you will end up in this sort of quadrant here. And you see that for run 93, which was a few months ago, most of the switches don't switch very much. But there are definitely a tilt upwards, which shows that we're not just sampling random designs that happen to have high scores sometimes. They're bona fide switches here. And I think the more we work on it, we're going to get more and more designs up here. So the good news is that it works, and the players seem to be able to handle the big throughput, which is very delighted. I was very delighted to see, because we were like 10,000 designs. Like, that's just too many. How are they going to keep up? And it happened instantly, so that was very, very pleasing to see. So I'm very impressed by all the players, and just seeing the solving of the puzzle earlier today, I kind of blew my mind a little bit. We were joking with it. I was like, wow, we knew that you were good, but that was amazing. So what we've done so far, as you all know probably, is that we started with these 6 sample puzzles. The exclusion ones are, again, things that turn off when you add FMN, and the same state turns on when you add FMN. The next round, we added the microRNA puzzles, because we think that going forward, microRNAs are very attractive targets, because we know how they pair with RNA, so it's easy to work with. And it's also very good to measure on the chip, because it turns out that the MS2 is kind of messy, and the FMN is a bright yellow liquid, so it's not great for fluorescence. So we hope that maybe we can turn our attention more and more towards puzzles like this. Now, based on the player feedback, we realized that maybe more important than just the sequence is how you place the different elements within your switch. So whether the MS2 hairpin sits in the middle or the end might determine how well you do. And so this is already, we got the feedback from the players, and it's good to see that we're sort of in this together. And that's why at the end of it, you won't see too much prediction of what we're going to do, because it's going to depend on how it turns out. The good thing is we added 3 more puzzles for the third round that we did. It was the latest one to be published, to see if we have learned something about the position. Finally, the one that's coming next week, and we took data all this week, is also taking into account all the feedback from the players. So Nando has been fantastic in making a new front end, as I hope you've all seen. So this one included the stampers for the next generation exclusion puzzles, which I really like that part. So now we have all the flexibility to put elements where we want them to be. And we also have the cooperative binding of MS2, which I'm also very curious to see if that binds out. And on the bottom cutoff there is the latest switch. So where we go back again, we give you one more chance to do the exclusion in the same state puzzles. Someone mentioned earlier this morning that it would be good to have staggered approaches, because it takes such a long time to get the results back. So that's what we started now. So right now we're back to give you a second chance, or I guess a fourth chance, to improve on these puzzles. And what probably is going to happen is that when that goes into production, we're going to enable some more of these next generation puzzles. And I'm not sure if Nando is going to talk about it, or but there's also great work going on in the background trying to make puzzles that actually lets you have more than one microRNA present and simulate the folding. So that's going to a whole new engine for calculating the RNA folding. So here is what we've learned so far. I think this was an interesting slide because, as you can see, players are really improving, which is great to see. What you see here is the 7 exclusion puzzles that we've given you. This is the first pilot round that we did, round 98, with about 500 sequences. This is the first big-scale production, and then this is the one we had a few months ago. And what you see here is the EteRNA score from 0 to 100 for all these different puzzles. And what I want to point out is that if you're down here, this just means that you bound the MS2, but it's at a very high concentration. So that's why you see a little bulge here. And the second bulge here is if you get the folding and the baseline step scores right, which means that it binds MS2 at a reasonable concentration, but it doesn't really switch. Then you're up here. So what we really care about is how much can we get up here that shows robust switching. And this is where you really see like a huge improvement, I think, for all the puzzles. Some of them are harder than others, and we don't really know why. It seems like the Broad's mod of Exclusion 4 was kind of similar to Exclusion 4, so it's not clear how much this positioning matters, if we can improve even further, or if it's just the fact that exclusion puzzles are harder. On the other hand, the same state puzzles were really encouraging, I thought. Here, on the latest round, we had plenty of them that got almost 100 perfect scores. So I would say that we actually solved this puzzle, so congratulations to all the players for doing that. We still have a chance to improve even further in the upcoming round. But I think we already shown that this learning works, and I think pushing forward to more than one input is doable. Finally, you see that the microRNA puzzles seem to be easier overall, and that's probably your experience too. This one is a sensor, so it turns on when you add the microRNA, and these ones turn off. But all of them show good results. And the important thing here that I like is that this is from Regis' class with his Stanford grad students who got this one. So what is clear is that the players are definitely beating the Stanford grad students, which is another good reason to use citizen science instead of some university-only cohort. So I would say that these ones also worked. So now we're going to give you a sneak peek of what we want to do. At some point a few months ago, we had a one-day session where we tried everyone in Regis' lab and also some players to solve the XOR puzzle. So here you have 2 inputs. In this case, we simulated 2 oligos, and we want the switch only to turn on when you have either one of them, but not both, and not when you have no input. And it turned out that that was really hard. So we tried all day long, and no one could do it. Nando made it. So congrats to Nando. We still don't know how, but apparently some other player. The rumors were that one player, in addition to Nando, made it. But the conclusion was that this is the hardest puzzle ever, and I tend to agree. I clearly wasn't using the fancy strategies of hula hoop and so on, but I think even that would be hard. So that's where we are. This is where we're heading. So brace yourself for some hard work. We think that hopefully with the information that we're learning with the simple switches that we probably run in parallel, we can incorporate many of the strategies and maybe incorporate them in like scripts or small helper bots that can guide the players along the way. So it's not always about every single base, but you can boost some automatically to focus on the larger scheme of things. So what we hope to do in the immediate future is to keep working on the microRNAs because they are very important markers in the body. They lot of diseases can be predicted by the population or levels of microRNAs. The thing is, though, that you almost always need several microRNAs sort of in a combo to really decisively say whether you have a disease or not. So that's where the multi-state puzzle is really, really, really interesting, I think. Now, in terms of Eterna, there will be continuing updates on the front-end side, so the gameplay itself. And I also alluded to the fact that we're trying to implement NUPAC instead of Vienna RNA. So it's going to be a slightly different engine. And I already met some players who said that some of these boosters and fine-tunings might be different. So that just shows that that's sort of the limit, state-of-the-art, or the state-of-the-art modeling that we have today. So prepare yourself for that too. But we hope to also add the scripts and boosters, so incorporating the knowledge of the players as we go along. And I think Vineet is going to talk about it later. So that's coming on the Eterna side. And in terms of the experimental platform, we hope to start using microRNAs also as an output. So instead of using MS2, use microRNAs. They're going to be easier, they're going to be brighter, and we hope to get better data using that. Hopefully more reproducible data where fewer clusters that are still forming. As we mentioned, we're going to have longer RNA molecules. On my side, that's down to me, is try to automate this even more to get me out of the question so the machine can keep taking data all over the night, so it doesn't just leave like me. And then finally, there might be some opportunities to maybe have even more colors. So instead of just looking at one microRNA binary, you can look at 1 or 2 or maybe 3 in the long-term future. So that's just sort of expanding the capabilities to match the combinatorial space of all the different ligands. And overall, we were very excited about this. That's sort of the near-term future to pilot this. But what we really want to do, and I think what Reed has mentioned early on, that we want to partner with labs, for example, at Stanford, that have interesting problems where Eterna can help. Because then we can bring our expertise and we'll actually see something that might be used with patients or for other purposes. And that one idea we had, it goes back to Adrian's talk this morning, of how would you make this sustainable. One idea would be, for example, where to have any intellectual property that comes out of it belongs to Eterna and or the players who actually contributed to the design that was picked, and have that as a kind of revenue to sustain the whole effort. And I think that that's discussions we still need to have, but that's a possibility. And I think the first example that we might try is to develop a diagnostic RNA molecule for sepsis. So we have a collaborator, Pravesh Khatri here at Stanford, who have found that a panel of 11 RNAs, so that's a big number, can use to almost perfectly predict whether a person has sepsis. And sepsis is a big problem and a huge cause of death in America. I think there might be 250,000 deaths per year, where your response to infection simply leads to death. And the thing here is that it's very time sensitive. So if you can find a molecule that immediately detects the number of RNA molecules and tells you whether you have sepsis or not, that hour or those 2 hours might be very important. So we think that that's a perfect starting point where we can maybe design an RNA molecule that senses 2, maybe 3 different molecules and give it a readout. So we hope that you're equally excited about possibilities like that, and we would love to hear your opinions about this, and especially if you have ideas of really good projects to undertake in collaboration with other labs, please let us know. So with that, I just want to thank, of course, again, both Reed and Will for letting me work on this, and of course the players and also the whole development team who's making this possible. So please ask some questions now, because after that we're going to go for the lab tour where we're actually going to show you this in practice.
So I just wanted to recommend a book. It's a popular book, but it might, you probably already read it, but for any of the players who haven't read, The Patient Will See You Now by Edward Topol.
Mm-hmm.
And it's thoroughly documented, the doctor, and it's all about the disruption of medicine and sensors, and what you were saying about your wife about personalization of medicine where you take control, and it's done at best as a partnership as opposed to the doctors in charge. And the discussion of instant low-cost sensors using microRNA and so on is very relevant into it.
Hey, I'm going to read it.
Yes. Just a quick question for the designs that you synthesize. I forget. Do you include computationally designed designs? Like,
yes. So we have been running EteRNAbot, or I guess EteRNAbot for switches that some of the submissions to Eterna are computationally designed.
And how they look comparatively to like players.
I think Joey's going to talk about it. I think sometimes they do pretty well. Sometimes they beat the players in one of the early puzzles, but I haven't pulled out the statistics yet. Hang in there, Kenny. Yes.
We're switching from Vienna to UPack. Vienna seemed great because there was a library that you could download and write your own code against it. Is the same available?
I believe so, but you should talk more to Nando. I think who's mainly in charge. I think it's an open source software as far as I can tell.
Joe can also
you have to sign up to download it, but anybody can download it back now once you register everything. They made the latest version open source.
Thanks.
And I think the code has been written like better than Vienna.
Well, that has to be true.
Yes,
just because I haven't been here, there's something that I don't completely know. I'm used to get. I know about how the shape data, like what we're getting from that. With the fluorescence, what's the difference in data we're getting as opposed to the shape?
Oh, that's a good question. So the main difference is that we don't actually know what the structure is. So the shape data is great because you know what every nucleotide is doing, if it's free or if it's paired. In our case, it's more a functional assay, so you just know if it, in this case, if it binds MS2 or not. And so it's, you essentially trading quantity for quality in a sense. But it does give you a functional readout. So if binding MS2 is what you really care about, then hopefully these data are good enough. And it also gives you a sense of affinity. So for shape, typically there's I think only like 2 conditions that you do. Whereas here you titrate the MS2 concentration, so you get more sort of qualitative sense of the binding of the molecule that you're looking at.
And how much of that data can be seen in the EteRNA interface? Because I honestly have one.
Some of it is there, like the EteRNA score and so on. But I think if you want all of the bit parameters on, there's a separate Excel sheet or a Google Doc. You can get 3 of those where I think all the relevant parameters that we put in.
Yeah.
And if you want the raw data, I can send it to you, but that's a big file.
It's 3 gigabytes. It's really nice.
This question goes along with the last question. Would it be possible to actually would you guys be willing to do this to take like a cross section of the designs that were done with the MS2 and do some and like do it so that you get shape data for those, just a few of them, and so that you can actually look at and see, okay, we know that these are pairing good, these are affecting good, but what's happening, and then that could give us a lot more information.
Yeah, that's a very good idea that we.
Yeah, data points to go along.
It's a very good idea that we've been thinking about. We haven't really geared up for it, but it should be very straightforward in principle because we know how to do the shape. And so it might be, we might maybe launch something where people can vote on which ones you want to do shape data on. We might be back to voting in that case because then it's in the slots, but I will let Luigi talk to that. He's the designer.
Just to comment on that, the kind of annoying thing about shape is we have to titrate. Well, I mean, if you want to see what's changing with the switching, which I think would be important, you have to titrate, and so the number of constructs you can do is much smaller. So it would have to be some voting system or something.
Yeah. It would just be like let's say five, like the top tier 3, and then like the middle 3, and
Yeah.
the bottom 3.
Yeah. I mean, I think that's a really great idea. Yeah. Okay.
We should do that.
All right, lab tour.
Yeah. Okay, lab tours.
So I think we're gonna, sorry.
Yes.
I think we're going to form groups of 3 groups. And I will take one, and Joe will take one. And we'll take one. So let's just number off by 3.
1.
Two.
She'll stay here to guard.
Okay, you can still be a 3. 2, 3. 1. 3.
1.
1.
We're both 2, I think.
Fair enough. Okay, that's that, and then we'll go. You're at 2. 3. Okay. 3. Sure. Okay. And 3. Okay, great. I will take 1.
And we'll take.
And we'll take
2.
2. And you will take 3.
I will take 3.
Yeah.
But
I'm starting. Fine. You're not everything.
Okay.
Where's 3 going?
I think 3 should go.
2, 3, 2.
No, and you should go to the my. Okay. And you know, you go.
I've never used it. I should split. I should split with Ann. I mean, I know.
No, you go down to the basement.
Okay. Okay. Sure.
And then I'll take 1 to the my secret. And so take. So 1's over with me.
Are they going to different labs, like different?
Yeah.
Like
That would be
she's always
two
doing
hundred.
here. Are they personal?
Everyone will get everything.
Yeah, that's what it is.
Yeah. I was just curious. 15. I know. Actually, 15.
15?
15.
All right. Awesome.
I lost my food.
Stop there.
want to set up?
Yeah. Should I just put this on top of the laptop or?
Let me get this out of the way. Probably plugged in here. Yeah.
Yeah. Dude, this is going so smoothly.
Yeah, surprisingly.
I know. we need to engineer one giant failure. So that people remember the EteRNAcon 2015 a little better. This is my friend Benham. He works at Google X on like experimental scientific projects.
Oh, nice.
And happened to be at Stanford for separate reasons. I said, why don't you come to EteRNAcon?
Yeah, for sure.
Next EteRNAcon 2016, you have to scan your badge. Yeah, it'll cost like $3,000. EteRNAcon 2015, you just walk in the door.
Like the analogous to the Google I/O. I think I went to the first Google I/O, which was like $50 for students, and now I don't know how many.
Yeah. Well, people claim that like I/O is sort of like destroying the company. It was like this one guy's idea. Well, let's put it this way: it's like the tail is wagging the dog. Like this one guy was like, "Oh, we should have a Google conference, talk about whatever." It was like a G+ thing.
Yeah.
And it grew bigger and bigger and bigger until like the entire company started like orienting itself around launching projects like that. Hey, am I allowed to bring my wife and son?
Yeah.
To dinner?
Yeah.
Okay.
Yeah, we've I allocated like for like 10 or 15 guests.
Okay.
Food group, yeah.
Okay, cool. I'm gonna bring. Do I sit down with us at the bottom? Or be embarrassed? Yeah. That's already happening.
I'm gonna explore lunch if you want.
I'm actually just gonna throw it to you.
Thanks.
One of the surprising things about the name Eterna, it's like the name Obama. Somehow it's like transmutable into like all other words. Like, what's an example? Well, with Obama. Yeah, I've got no good example. It's like Obama, you Obama. Like I don't know what. Like you can always like there's like a way of turning Obama into like anything. Like you turn a con, you turn a script. I think it's the final vowel syllable.
Oh yeah. Yeah, it's eternal con.
Right. Have you heard of Moderna? No. Is that what it's called? Moderna? Do you know what I'm talking about?
That sounds familiar.
The RNA company that raised $500 million.
Yeah, the mRNA, right?
Yeah. What's it called? Moderna?
Moderna, yeah.
They do the same RNA trick as us.
Hello?
Nope. Yeah. Sorry, dude. We need to look you up. Yeah, we didn't bother to patent anything. I'm not sure if it would be patentable. Well, actually, Will Greenleaf may be pursuing patents for this stuff. I don't know.
It's very tricky though because he's using Illuminous.
Yeah, maybe patenting like.
The design.
What's that?
Just you give just the design.
Right. Yeah. Exactly.
But like you say, what's going to be cool is when you have like a player patent.
Mm-hmm. This is what we've been talking about recently, like, so just speaking of like different businesses that can model like, the players of EteRNA have already come up with like non-trivial new knowledge about RNA that was not in our that's published. And so the question is, can we get them to design non-trivial trials? You know, right now it's been much more of a small scale experiments and stuff. Can we get that non-trivial? Like, and if that's the case, what's the IP status of that? Like, who owns it?
Also, if you're going VCs, or are you?
Well, so I didn't mean to scare the audience into thinking that we wanted to, that we need to talk to VCs to fund EteRNA. I really don't think so. I don't think that'd even be a good idea. Even if you wanted to fund EteRNA commercially, you might not want to do it for venture capital. What's that? Right, but if you, so there's many ways of raising money outside of venture capital. Like you could raise it directly from pharma companies, or you could do what we've done, which is raise it from the government, from like NIH or NSF. And then they're all different structures. But basically, typically, like if you, from what I understand, you know, if you went to a VC, they would want the company to own the IP, but then they own the company or a percentage of it. So from their perspective, it's more valuable if you have more patents. Right? It's not like they don't want to own the patents; they want you to own them. And they want it. So I think the reason why I was sort of talking about it is because, like, I mean, I was just trying to think of a question that I thought would be interesting to both me and the audience. Yeah. Okay. Cool. I'm really glad to hear that. And you know, I have myself for the past like 10 years basically been like involved in like really what I think is cool and fun science, and often like the goal is to just advance science or do things really cool and wacky and stuff. And then recently, having moved to California, I've like talked to friends who are business people and VCs and stuff, and it's actually like astonishing and astonishingly beautiful in some sense how little they could give a shit about any of that stuff. And they're like, it's just numbers on a spreadsheet. Like, you should tell me that, like, you know, V4 is going to be larger for your company than it is for any other company. And it's actually, it's very democratic, actually, very equalized.
It's also really saturated.
Saturated in what sense?
So, I mean, I can see why it is. It's appealing.
Right.
But what they
Yeah, and again, I really don't want to, I don't want or expect ever to fund EteRNA itself through venture capital. But I think that would be a terrible idea, actually. But I do think that venture capitalists ask questions that ultimately anything that needs to survive in the long run needs to be able to answer. What's that?
question of what would make the project successful.
Yeah, what would the project like make money? That's where we're running from. So it's like if we're doing all this work and we think it's valuable, you know, in science we could write papers, and that's valuable. But in society, it's more like you attach a price tag to it.
I'd like to see an open source concept.
Yeah.
You can still get credit.
I know. I mean that. Yeah.
The problem there is like the
Here,
whole technology for that is the whole like bureaucratic like infrastructure for this is kind of like far away to like actually make it like everything open source.
But there was. I mean, I think open source is like a great example, right?
Yeah. What?
I mean, like in the 70s, for example, like all code was like proprietary and written for giant corporations. I mean, actually, no, that's not true. There was already Unix and stuff like that. But so basically, that's the case. And then now, for like a huge percentage of projects, you know, it's basically given out for free. And like an economic model has arisen around that. I mean, that's the interesting thing, right? nothing can ever exist in this world indefinitely that doesn't make money. It's just literally impossible. It violates law. Yeah, exactly. Like violates laws of nature. So ultimately, if you want to do what you're doing to be successful in the long run, it just has to make money. It's the rule of the game. So until all this open source stuff does actually make money, but in sort of a funny way, like reputationally. You know, people write open source code and get hired by the big company, you know, and that kind of thing. So what would the answer be for what we're doing? But yeah, we want to keep all the good stuff too, like the, you know, open access to all of the models that are designed. Transparency in terms of how the data is collected, you know, everything.
I don't recall what it is.
Just like the for-profit for good businesses. Is that what it is? Yeah. 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 It's an interesting idea. That would be very cool. I don't exactly know what the legal implications of that is. I think it has something to do with like shareholder rights or something like that. What's that? Oh, really? What? I actually don't think I've met you before. I actually go say hi. Just be like. What's that? Oh, Marie. Oh, whoa. Oh, you look different.
I should recognize you.
Behind your sunglasses. How's it going? Thank you. Yeah, well, basically, you're walking inside.
Actually, so
I think it would be nice to. I think you just. Hey, how scheduled is tomorrow?
Not all day. It ends up early. Ends up like at 2:30.
Oh, right.
So that would work. So then
Or time we come to the last section.
Yeah, so the last kind of session in general, it's like from 1 to 140-ish. And then we have like an open forum, so socializing, then we can do.
Okay. And what time is it?
2:15 to. Okay, so maybe we should do like 3.
I think you're using the deprecated capitalization of EteRNAcon.
All right.
It's now all lowercase.
Is it? I thought we should like enforce it again.
Oh, really?
So in my recent paper, I just enforced it again.
Oh, man. Okay.
I have no idea.
I always wanted to enforce the no period in fold.
Oh, there's a period.
Everyone was spelling it fold.it.
That resolves to that's the URL.
That is the URL.
Actually wrote a micro on my computer. Everyone started doing lowercase.
Oh, really? That's really funny. I basically realized that like Eterna with the capital RNA, everyone pronounces it EteRNA. / the fact that there's RNA in the name Eterna, we don't need to call it out. It can be like a little secret that you realize like after a while, you know?
Honestly, like I thought that the RNA was capitalized and usually helpful, so I started verbally trying to explain about the project, and I can't say RNA was
Oh, right.
so.
Eterna. Like competing game. I actually wanted to call Eterna like make it as like a
Instead of
as like a successor to Folded. But then I didn't want to weigh into the pot. Like so many cooks in the Folded kitchen. It's like they're all gonna get all touchy about this, so let's give it to them. Yeah, that's true. That's true. I'm not even sure. We probably wouldn't have been able to get the name. It's astonishing that we got Folded. Actually.
Determine is good. It's like too good to be.
That was part of the name. Interestingly, so my grad student starting this company that you saw, and so my other friend who started the company was like, you should meet my friend who names things. This guy's a naming consultant. He charges $15,000 for a name for a small startup. So
Does that include the domain registration?
What's that?
Does that include the domain
It actually does. It includes international search. They also translate the name into like all languages to make sure it doesn't mean like Phuket or something in like Chinese, Swahili or something. But he's named some big stuff. He named Young brands.
Really?
YUM, yeah. He named Qualcomm Snapdragon. And some stuff you've definitely heard of. Like he's like one of the top like 3 naming guys in the country. So basically, we don't want to pay that kind of money for us to start up. So he said, okay, well I'm going to give you this document which explains to you how I did it. I was like, okay, so we read the document, and this is how it works. So what you do is this is how they named the Qualcomm Snapdragon. They go to Qualcomm, they give them the design brief. So the design brief says this is a new chip. We wanted to, all the chip names up until that point were sort of like pseudo-Latin, like Pentium, like Athlon or something like that, right? So they're like, we don't want it to sound like pseudo-Latin. So we wanted to stand out. And then the chip has all these properties. You can do multiple things at once, and it's very speedy, and you can use it for graphics and all that sort of thing. Okay. So then what they do is they list painstakingly all these attributes of the chip. Then they forget that there's a chip, and they think of other objects that have those attributes. And they came up with a list of those, and the one that won was a circus. Then they rewrite the design brief from scratch for a circus, and they translate all the stuff about the chip into circus talk. So they're like, there's 3 rings, and the audience loves it, and it goes through town, and it comes really fast, and there's like all this stuff. And then they hand the design brief to a team who doesn't know anything about the chip, and their job is to name the circuit. And they came up with the name Snapdragon, and that's how the chip got named Snapdragon.
That's a lot of work for.
You know, this guy charges a lot of money, so.
A lot of mouths to feed.
Yeah.
Process.
But I think, yeah.
There you go. That's your reputation making you money. That's the open source.
This guy is not just all right. I think this guy is good, man. I think he truly has like a talent for naming. Yeah. Is that what you're talking about?
Yeah.
No, I think this guy would actually be worth it. And $15,000 is really cheap. I think actually, like he charges big corporations a lot more. But
I mean, just the name, like the name shape, right? Or the RNA stuff. But this guy can make weeks, and so if you actually go to like the a basic like nucleic acid chemistry book to find you can find the same protocol he uses for like superhydroxyl attack for with primer extension for nucleic acid structure interrogation. That technique has been around like 20, 30 years. But he named it shape, and he's a marketing in terms of like science marketing, he's pretty good. So
Right.
that's his career actually.
Shape accessibility mapping.
Yeah.
Well, we.
The opposite one right now was still similar. You're dealing with binary research. Sometimes you like wall and trying to describe the concept. You literally have to create a word.
Right. Well, that's what I mean. That's what we've been advised at this company, which is basically like unrelated to EteRNAcon, which is basically like you need to. It's critical to name it, if only so that others who talk about it can like refer to it in one word. So it's about. I think it's a really fundamental element of the name. Yeah.
That's your tour. I'm going to do that.
Yep.
Different guy.
I installed it and I never figured out how to run it. So I actually have charge him a small amusing amount. Instead I just make very nice things.
I dug through your little bit, but I think I more or less know.
Wait, you wrote
term or not entirely. So basically, most of the time, as far as EteRNAcon is concerned, you get like oh yeah, like when you start using Drupal as like database, like we have to like change it.
No, the actual term. No, Marta, I really want to know why you think that.
Ninja. Yeah, you should give you're the earliest developer. You should give like a 5-minute war story. Like for example, Ninja was the guy who wrote the Facebook integration.
Yeah, like the whole literally.
It was just like, yeah, basically, I remember it was like, Ninja was like,
which would do though.
Yeah. And I was just like, I didn't know that's what it was. But all the people go down there and break it. I was like, okay, see you guys later. And then Ninja Gopi is like, I can play the phone when they're break. And I was like, are you sure? And he's like, yeah. And I was like, well, it's a good great. He's like, yeah, no problem. 3 days later, we had like amazing things. But
yeah.
No. And then it was like hectic because Facebook was going through this like phase where they were changing their APIs. So it was like it was changing almost like per 2 weeks. Oh my god! No, I mean,
maybe they're good. You want to give like a 5-minute every day.
I don't know.
Yeah.
Yeah, I mean, want to.
No, we're.
I like created my own code at this point. Everywhere. Oh yeah, it's great because like I already have like other stuff to do. It's good that you guys join the song. Bill Packard was sponsoring it's just straight. It's not like actual like. I wrote it when I was in like. No hard stuff. I'm not sure how the dictation of like importing is kind of weird. It's only like accepted. They didn't like give us binaries so we had to like the other website and whatever. Yeah, like and then I had to use my phone downline to access the inbox. Yeah, I'm pretty sure that later they changed this because they got the binary back in the day.
Yeah, I know. I can get one of these answers.
Yeah, their server and then like they give you both email. Yeah, so it was like they give you after as a result page sometimes like wrong data on it. So like I had to like get an email 3 months and we apply which works in the server and then ours like use they have their own paper system. So each keystroke you can every single keystroke 3 times do whatever operation you want and export via inbox to a certain text file.
Dude, he made these like
But
So if you like email them, or
So I told Ryan for the other day, it's gonna be like 10 minutes long. Yeah, I mean, I have a question. Sorry, I was like really stressed. You're doing a really good job managing everything. So. Yeah, I don't know. All I know is like kind of like. Yeah, I haven't started this page. Sorry, guys, I'm way crazy. It's very good.
Actually,
we're supposed to start at 3:30. Yeah. Well, I already stole some.
Are you ready?
Yeah,
Ready to get started?
So, should have had.
Okay.
No, I don't.
Okay, great. Ready? Okay, I think I have -6 minutes left, so I'll try to go quickly.
Don't worry about it. Like, we have some padding time.
Yeah. Okay. Well, I wasn't serious about going. Okay, so I'm going to talk to you. Well, first, let me just say thanks so much for the introduction. It's super exciting to be here and see what you guys are doing, both as players, as developers. It's really inspiring. And I do think this is the seed of something very exciting and quite powerful that it'll be obvious in the future, but it's great. It's also really fun to be at the beginning of these things before they get turned all corporate. So I love meetings that fit in this size of a room. So I'm going to talk to you about nanoscale tools for cryo-electron microscopy, which, if you're not familiar with this technique, I'm sure you will be soon. It's actually it's revolutionizing structural biology right now after about 30 years of development. So it's another one of these technologies that started a while ago and is really picking up steam now. And we're trying to build tools to improve it. And that will be relevant to Eterna, as hopefully I'll make clear from my talk. Okay, so my alternate title is This Figure Will Make More Sense in 10 Minutes. Okay, so our goals in my lab at UCSF is, one is really to understand how life works at the nanoscale, which is quite a broad goal. And the second is to invent nanotechnology to help achieve this first goal. And so I always like to start with the big picture question of why are you doing what you're doing? Why are we developing nanotechnology? And one way I've been thinking about recently is that when we invent new tools, it lets us extend beyond human capability. So, for example, with our eyes, that are these amazing organs that evolved over many millions of years, we can see the visible spectrum of electromagnetic radiation, 400 to 700 nanometers, which turns out to be really useful for surviving. And for a long time, humans didn't really know what things looked like that were smaller than what they could just see with the naked eye. And then they developed optics, and we extended our scope to kind of milliscope, which we call magnifying glass, and then later microscope. And now the nanoscope is really the cryo-electron microscope. And so the way we know that there's kind of the world beyond what we can see is by building tools. And while seeing is believing, and is really useful for kind of looking at how things might work, I think that understanding really comes from playing with things with your hands. And I'm not the only one who thinks this, but you know, when you look at a child learn how to interact with the world, they want to grab onto everything and touch it. And actually, one of my first memories was burning my hand on a kerosene lantern that I thought was glowing in a really interesting way when I was 2 years old. And everybody told me not to touch it because they had this experience and the memory of, you know, something that's hot will burn you, but I didn't have that. And actually, I had to touch it to understand what it was like. And so that works on the macro scale. And what we're trying to build are the nanoscale equivalent. So if we want to understand how things work on the nanoscale, we kind of need hands at this length scale as well. And we're using DNA to build our hands. Why do we build with DNA? Well, it's a really relatively simple material that enables self-assembly that's programmable. And this field was pioneered by Ned Seaman over the last 30 years. And the field that's come out is really quite exciting, and it's a great community, and I've been a part of this community now for going on 10 years. And the way we build with DNA, or at least the way we do in our lab, is using this method called DNA origami, and this gets us about 100 nanometer length scale nanostructures that we can design and fold out of DNA. And this method was developed by Paul Rodeman at Caltech. And I'm not going to go into detail. There's many thousands of citations of Paul's paper and lots of stuff online if you want to check out more. So this talk's not really about origami. I think those of us in the community have already heard about it a lot, and there's a lot of things online. So you can check that out. But I do want to talk about our potential applications of the technology and in the context of kind of seeing how things work, and also in the context of our goals that I mentioned earlier. So as I was saying, this electron cryomicroscopy, or cryo-EM, which is kind of confusing transposition there, is this amazing tool for seeing on the nanoscale, and the literature is starting to bear out this advances in the method. So we're starting to see near atomic resolution of structures of viruses, of the ribosome, and actually recently this ion channel from my colleagues at UCSF, the TRPV1 channel. And so here are some class averages of what this channel looks like. And everybody, well, I think everyone in this room actually has this channel on their tongue. It's what we use to sense caspacin, which is the molecule in chili peppers that this actually kind of jams open this channel. And so when the caspacin is bound to the channel, you perceive the same sensation as you do from heat, because it's also a mechanosensor. So that's kind of cool. And then actually just earlier this year, they solved this TRPA1 channel. It's a related channel. And this actually has a different shape. And I think these structures look really cool. Looks like a little tooth or something. And you can see it from down the end, or like through the top of the channel on the right side. And this channel binds the wasabi pepper. So you have different channels that are different receptors that bind to different chemicals, and we can actually understand how they work now based on the structure. And so this is the kind of seeing things and then understanding how they work. And what we want to do is build new tools using DNA origami to improve this method. Or in other words, we want to build the hands that will aid this kind of visualization method. And I'll tell you what I mean by that. But before I tell you how we can improve this, I think it's useful to learn a little bit more about this technique. How does it actually work? And then once you know how it works, you can better understand how we can improve it. So this is my quick crash course of cryo-EM. And so that's our target sample, right? This is the structure we're trying to solve. And this can represent a protein, an RNA structure, a DNA structure, or a complex of all of the above. And the first step, which maybe takes like 3 to 10 years worth of biochemistry, which let's just assume that's already done, is to prepare your sample nicely purified and clean in your test tube. The next step takes only 5 minutes, which is to put this on an EM grid. And so we can zoom in and imagine what this might look, diffusing around in a little droplet on that grid. And so what we want to do is actually remove the excess sample and then freeze just like a single, like 50 to 100 nanometer thick layer of our sample, and we freeze that. We convert it to ice, basically vitreous ice, and the way that this is done is with a special instrument called a VitroBot, which actually it resembles this monkey with 2 symbols, and the sample goes right in the middle. It actually does look like that. So this is the instrument. I should get a movie of this, but what happens is the symbols kind of clap together and blot away the excess liquid, and then the tweezers plunge the sample into liquid ethane, and everything freezes, and you get this very thin layer of your sample. Next, you load your sample onto the microscope, and this is a bit of an involved process, but once you get that into the microscope, the electron cryo microscope, you can shine a electron beam through your sample onto a detector, and we get 2D projections of these of all these individual particles. And it's really the advances in the detector technology and the software that we have to process this data that's really pushed the resolution recently of the technique. So what we do is then use software or manually pick particles. We throw away the bad particles and then align them into class averages. So individually, they're kind of too low contrast to do anything with, but when you stack them up, the noise cancels out, and where there actually is material, you can see. And once you have these class averages, you can use this kind of back projection method to get a 3D reconstruction. So hopefully that makes sense. Okay, so now you know the method, what limitations can we tackle if we had hands that could really grab onto these samples and orient them? Well, the first thing that's obvious once you start using this method, and you can actually see the pattern in the literature of what people have been able to solve, is that small targets are really hard to solve with this method. And the challenge is that particles less than even 200 kilodaltons are really difficult to resolve. So the small ones are actually tough. And the reason is that we have these very low contrast images that come out of the data. So let me just show you some actual data from Yifan's lab. So this is the TRPV1 channel, and this is a 300 kilodalton complex. So you can imagine something a third the size or a sixth the size. It's going to be really hard to pick that out of background noise and actually assign it precisely to a class that's different from a different class, which is maybe rotated by a degree or two. Yeah, Adrian?
Can you tell us what a kilodalton is?
Kilodalton, so this is so kilodaltons is 1,000 daltons, and so if you okay, sorry, this is a tech, yeah. If you look at, so like a base is like 330 daltons, right? So if you think it's molecular mass. So if you look at the periodic table, you can see everything's mass all the elements mass, and usually in daltons. I'm not a chemist, so I can't tell you anymore. But yeah. So, but it's kilodaltons, like in the 20 to 50 to several hundred kilodalton range, is like the size of proteins and RNA complexes. Megadaltons are considered large. They're easy to see. Smaller than 100 kilodaltons. And all we really care about here is relative sizes. Less than 200 or 100 is going to be below the size limit of this method currently. And the average protein mass in the human proteome is 50 kilodaltons. So more than half of our proteins are too small for this method. So, okay, so can we enlarge these samples with DNA nanostructures? We think the answer is yes. And the idea is that you kind of build a life preserver and you dock your target structure to this this origami structure, and then that provides the contrast. It's easy to see and pick these nanostructures bound to our targets out of that data. Okay, the way this translates into DNA origami is this kind of frame structure that could incorporate a protein or RNA binding site, and then this will increase the effective mass of, say, of some random sample that we're looking at, maybe from 50 to 2,500 kilodaltons. So that's going to give us much more contrast and make it easier to hopefully process and solve the structure. And I want to mention that this concept is something that's inspired by work that originated in Hendrik Dietz's lab, and we were in the same lab when I was a student. He was a postdoc, and a lot of people have been talking about this kind of improvement to the method for a while. And so, Thomas Martin actually led the original designs on this project, and he's now in Shores Shares' lab at the MRC in Cambridge. So a number of different labs, including ours, are working on these ideas. And so now I just want to tell you, how do we make this in the lab? And this is going to just be another quick DNA design crash course using CAD Nano, which is software that I led the development of as a student and postdoc. So the first step is actually to design a structure out of DNA that's going to enable us to kind of dock our target to it eventually. And so what I'm showing you here is the CAD Nano interface. And I'm not going to go into detail about this just in the interest of time, but suffice it to say, this is kind of 3D DNA drawing software. And there are defined rules that we use, that we developed in the lab, that allow us to kind of design DNA sequences that are going to fold into a certain shape with pretty high reliability. So what I'm showing here is that we're trying to kind of recreate this frame shape just using the CAD software. And actually, I'm just going to speed this up a little bit. And So what we do is we kind of figure out where we want this kind of long DNA strand to go in space, and then we design a bunch of short strands, and then eventually we're going to want a binding site, and we're going to put that right in the middle, and then assign sequences to everything. And so what we end up getting as the output of the software is an Excel spreadsheet with a list of DNA sequences that we can then order from a vendor, and we get 96 well plates of DNA oligos in the plate. We pull them together, mix them with other pieces of DNA, heat them up in the PCR machine to about 60 degrees. That's like a hot cup of tea temperature, and then gradually cool them down back to room temperature. And then at the end of this process, we get many billions of copies of each nanostructure in about the size of a raindrop. That's our test tube volume. Okay, so this is a great fun process. It's accelerated with the CAD software, and what we're really excited about doing is designing structures that will do useful things. For example, here. So what does this actually look like when we put it in the microscope? Well, here's the preliminary data off the cryo-EM. So just to remind you, this is what TRIP V1 looked like, and you can see that these structures. This is not great image quality on the projector, but they're unmistakable, right? You can spot them, you can figure out kind of what orientation they are, and you could definitely figure out where's the kind of aperture or the spot in the middle of that frame. And that's where you would look for a sample that you had bound to it. And then you could go on further to solve the structure of something that was bound rigidly inside. We can now start taking class averages. So this is what this looks like when we stack up these images and average them out, align them. And what we've started to do is take DNA binding proteins like this TAL effector, transcription factor, and dock that to its recognition sequence, which we put in the middle of the frame. And this is now not cryo-EM, this is negative stain, so it's not as high resolution and a bit noisier, but at least you can start to make out this kind of little worm wrapped around the double helix right there. Okay, so what we're working on is optimizing this method further. We want rigid attachment of diverse targets, and I put an asterisk there because I'm going to come back to this where it's relevant to the Eterna community. But I want to mention another limitation, just kind of building off of what Will was talking about earlier. Throughput is very important, especially if you have thousands or tens of thousands of different designs from a community. And so this is a very low throughput method so far. So one structure might take a few years to solve until recently. And there's many things that go wrong. And actually, nothing really is hard in science. It's just there's a lot of potentially easy steps that add up, and you have like 1,000 or 2,000 things, and you need to kind of get all of them right, and then you get a result. And that's the hard part, is putting all this stuff together. And so, here are a few examples of things that can fail. Your sample that you started with that it somehow goes bad, or it was good last week and now it's no longer good. The grid is not good, or like the humidity conditions were not right, and so your ice was too thick or too thin. And a common one for us is that the microscope is just broken. So you do all these steps, and then you finally get ready to image, and it turns out that the microscope is broken for a month. So anyway, what if we could just like image all of our samples at once? If we pooled everything together, mix them together, and there's plenty, like we can image 1 million particles at once on the EM, but we might only need 10, 20, 30,000 particles to solve a structure. So there's a lot of space that we could be using that we're kind of wasting right now. So what we want to do is actually pool everything together and then barcode those samples in advance, so then we can sort them back out during the image processing step. So it's sort of the equivalent of adding a DNA sequencing tag that we can then use to later tell apart which spot is which on the array. Okay, so how does this translate to DNA origami? Well, this is a project that a former student in the lab, Stefan Niekamp, worked on. And so the concept here is that we add additional little modules that we refer to as barcodes to the frames. And then now we can they have sort of a QR code-like appearance that we could we can then easily sort out during the image processing step and just bin those into their appropriate categories, and then do the downstream processing. So we've actually showed that this works using negative stain. So we made 16 versions of a 4-bit barcode, pulled them together, imaged them in one EM session, binned boxed all those particles, and then ran them through the image processing pipeline to sort them back out into their class averages. So this behind me is the representative image, and then the class averages of those barcodes. And so in principle, we can hook this up to the frame and then put 16 samples onto the cryo-EM instead of 1, which would be a major upgrade. And then you can imagine we can do more in the future. I just want to go briefly through the barcode design. I think it's kind of cool. So this is just to not spend too much money on these designs. So we actually have a single design for every barcode, and we just we route the DNA in a way such that when we fold these different domains, we add one set of DNA oligos or a different set, and depending on which ones we add at the folding step, we can toggle this little bit onto like the on position or the off position. And so these two designs are actually just kind of the same core set, and then these different bits are toggled on or off depending on which oligos we add at the pipetting step. So anyway, we're working on attaching these to the frame so we can actually use them together. We want to validate this with kind of known structures and then solve novel targets, and in particular RNAs. And so this is where I want to come back to this technical challenge of how do we attach these RNAs. And Mia Salins, who's here in the audience today, is working on this. And so there's a few different ways we can imagine attaching RNA nanostructures to these frames for 3D structure determination. So one obvious one is DNA sticky ends. So we just have a 5' or 3' end that's complementary to whatever is on the design. But you could imagine that you quickly run into limitations there. So what if your structure actually requires the 5' or 3' end to be engaged in the active site or something like that? So these are definitely, that's like the first obvious option. But what we also want to work on are using our RNA binding motifs, either RNA itself or proteins, and this is what Mia is focused on, is adding basically handles or something inside the frame that we can use to rigidly bind to those RNAs and dock them to the frame. And so how's this going to work? Well, so here's this protein. I was showing a RNA or a DNA tag, which I'm going to just get rid of that because we haven't put that on just yet, but we're working on it. So we'll have to attach it to the frame. But for now, we actually want to study kind of how can we build useful protein library that can attach to different RNA designs, just to give you guys more flexibility in terms of what you can use in terms of sequence constraints. So we've selected this L7AE protein, which is a ribosomal protein that binds with really great affinity to this kink turn motif. And so this is a small 12 kilodalton protein. It sticks really well. It has like 1 nanomolar affinity, or better. so this is like potentially a great binder for RNA sequences. And then if we zoom in here, this is what Mia's been looking into, is kind of what are the interacting residues and how can we start mutating these. So we have kind of our wild type. Can we vary those amino acids and then also vary the RNA sequence in the kink turn and build a set of mutants that will bind to different sequences that will increase our flexibility in terms of what we can design with. Hopefully that's clear. And so what we're hoping is that we'll have a platform, maybe in the next, by the third time we have this meeting, where we could actually start taking player designs, dock them to these nanostructures, and actually give you 3D near atomic resolution structural data to complement the shape data and all the functional tests. And so I think with all of those together, you'd really get a much more complete picture of what's going on with these designs, and a lot of things that we just can't see with chemical mapping. would become obvious if you can just look at the thing. And with that, I'll just finish and say this is the kind of outlook for the project. We want to complete our library construction, characterize it, hopefully in collaboration with our friends here at Stanford, actually solve some new structures, hopefully using the barcodes for high throughput, and then maybe start talking about using player designs and putting those into this platform. So I'll just thank my group, and I've highlighted the people who've worked on aspects of this project so far, and actually Terrell is working on this as well. And thank you to my funders and past collaborators, and thanks to you for your attention. I'd be happy to take questions.
What orientations do you need to get?
Yeah, so the question is when you're solving a cryo-EM structure, how many different orientations do you need of your sample in order to solve it? And so I showed 3 for simplicity in my slides. Usually they're like I think a couple hundred class averages of different orientations, but I think the more the better. But if you have, I'm not actually sure what's the minimum that's required.
When you're holding it in the frame,
yeah,
you imagine these will land in the same orientation every time, more or less. Is that true?
If you have a solid support that they're sitting on, but if they're just diffusing around, yeah, like in the droplet. So I was showing them as flat, but then
in the true cryo runs, they'd be random because they'd be vitrified.
That potential, there's a number of things we could try. So one is we could attach them to the frame, then we figure out a way to maybe release the sample so it still hasn't diffused out of the frame, but it's in a random orientation. Maybe it's just a cage. There's a lot of different things we could do if the orientation bias is an issue. But another thing we've been thinking about is designing a series of frames where we predetermine the orientation and we make like a little grid pattern. So you could just like already know what the expected angle is, kind of like this gimbal idea. So there's a lot of kind of virtual tomography, many different frames that would, so you pull together, say, 200 different frames, each with different Euler angles, how they orient the sample. So, yeah.
You were talking before about how with the smaller molecules, how the resolution impacts you being able to actually locate where it is. Might there be a problem with resolution just being able to get your resulting 3D image because the resolution is too low to be able to get enough detail out of it?
So your question is, I'm sorry, I don't understand your question.
Is there an issue with resolution, not just that you can't find it, but also that you can't actually get a resultant?
Oh, yeah. So in general, the resolution of, so the question is, what are I think what you're asking are, besides finding your sample, what other factors limit the resolution of the technique? Or are there other issues besides just finding your sample? And yes, there's many potential issues that could limit your resolution. So there's like drift of your sample, there's beam-induced kind of fluctuation. Actually, everything sort of seems to move around. Even though your sample is frozen, the image moves just because of apparently electrostatics that build up on the grid, for example. So these new detectors, which take like 400 frames per second, they build up these movies and they sort of have these image stacks where they do corrections. Yeah, there's lots of, there's so many different things, including, sample heterogeneity. But I think the take home is that the method in general has improved to the point where various really expert labs around the world have been able to solve near-atomic resolution structures that are starting to compete with these really well-established methods. And then moving forward, you're going to see similar resolution structures for targets that have been inaccessible to other methods, such as crystallography or NMR, because those samples might be too flexible, or they just like are never happy forming crystals, or they're the wrong size, or something like that. So the potential of the technique is that we can actually start seeing things we've never seen before. Yeah.
Obviously, obviously you're pushing the envelope, which is very cool. Is there any prognosis on cost trends? Is this likely to be highly expensive initially and then decline, or is it already? Anything you can tell us on that?
Oh, yeah, like, do you want to buy your own microscope? Or yeah, like, so the microscope is research in general is always expensive, and almost by definition, like, cutting edge research is just expensive, because if it were inexpensive and easy, that wouldn't be research, it'd be kind of routine, right? We'd be making money off of it instead of spending money. So the microscopes themselves are a few $1 million. The camera is $1 million at this point. The service contract that we have at UCSF is $250,000 per year, and then all the people like training them to run it it's not fighter jets, right? But it's not like DIY either. It's like somewhere in between. And so part of the goal of making this high throughput is to bring down the cost using existing infrastructure and extend it to targets that maybe people wouldn't normally be able to afford time on the microscope. But that's like the limiting factor right now, is just getting time on these microscopes. And there aren't enough people in the world trained to set them up and run them right now for the demand. So it's similar to what DNA sequencing and all these other great techniques were years ago. Like it'll get better. This is sort of as bad as it will ever be, I think. And yeah, so I'm optimistic. Yeah.
In your one image of the receptor, the TRPV1,
yeah.
Was that image the one that was used in order to generate the structure that was like 4 angstrom resolution or something like that?
Yeah, so this is just directly from the paper.
So then, in your own image, what sort of angstrom resolution are you expecting to see when you actually make those things that, to be fair, you predicted beforehand structurally?
Yeah.
But if you were just to analyze them blindly, would
Sure.
you come up with an angstrom resolution that was like 1 angstrom resolution or something?
Oh yeah, so the record for cryo-EM is 2.8 angstrom so far, and the record for DNA origami using cryo-EM, I think it's like 4 angstroms, and that was the Dietz lab and Shara's together. They made these origami structures, and they see kind of in the middle core of the structure, they get the highest resolution. It's the most rigid, and as you get towards the edges, it becomes more fuzzy. And so we're just in the very early days of figuring out how to get high resolution structures. But the resolution of the origami structure may or may not limit the resolution of what is in the middle of the structure or what we have bound to it. So, So I think what we'll get, it'll be high enough to see what's going on in the future. I don't know how long that will take, but I'm optimistic. And I have my neighbors are like Yifan Cheng, Adam Frost. These guys are super expert at, David Agard. They've been pushing this method for the last decade. And they're the ones who kind of, help get us to where we are. So we're going to keep pushing it further.
Thanks. I was just, I guess, so the angstrom resolution of the outer structure can be translated into the molecule in the center, just because that thing is now more rigidified.
Well, what I'm saying is there may be different domains or different parts of an origami RNA complex. And if the RNA itself is rigid and we can figure out how it's oriented, we might be able to get a higher resolution structure for that part, even if the origami itself is flexible. So I'm trying to respond to what I think might be your concern is if we can't get high resolution structures of the DNA, or if the DNA is flexible or something like that, is that going to limit the overall resolution of the technique? Mm-hmm. Which I think it probably won't, but we'll see. Okay, so no more questions.
Just one more.
One more? Okay.
So how many, if in EteRNAcon 2017, how many structures do you think, or how many designs do you think of, extrapolating like a...
From 0? Probably one.
Do you have do you think like it's 2017 like Facebook?
Okay, well, I'm hoping for at least one, let's say. And then once we have more than that, then we can actually start extrapolating. But so far, we've just put all these different pieces together, but we haven't solved any new structures yet, and we haven't even really pushed the resolution yet of the things that we're in the validation stages right now.
And so this idea of barcoding, I don't follow the Quantian literature so much, but like, is it that people like done already like resolved 2 or more structures in one sample?
I think that people have been able to detect different conformations of the same protein and throw away the conformations that they don't want, or look at 2 different, solve kind of different versions of the same protein. But I don't know if they put totally different samples together, not to my knowledge.
Thank you.
Okay, thanks.
Okay. So for the panel, we'll have Nando, Jericho, I'm going to ask Vinny because he's also there, and Michelle from our group. So, on board.
Is dinner after this? Yeah, so there's dinner after this, so you can call Joseph.
So is this just a mirror image? Okay. Can't see my notes.
I would. Do you want to see your notes?
No, okay.
You can connect to your.
It's okay. Yeah, it's like only 10 minutes long. So. Okay. Okay, do I have to talk to this thing?
Yeah, but I think it's my phone.
Hold it?
No, you can. You have Will?
I don't know. But like on the phone. Yeah. Alright. Where put this? Oh. Alright. Okay. And I'll just go. Oh, does this thing work? Whatever. What? Oh, yeah, that's what I'm looking for. Is this the laser pointer too?
No, there's no.
All right. All right, can everyone hear me? Okay? Okay, good. All right. So I'm going to give a short presentation on what's happening with automated algorithms, or what we're calling them bots, within EteRNA. I'm going to just briefly talk on all of the algorithms I'm aware of that are in EteRNA now, and some of one of my pet projects that I worked on when I first got to the DOS lab. And then I'm really hoping we can actually just have a short talk and then have a discussion about where we would like to use bots in the future and what people would like to see from them. So I'll start off really general. I don't really have to tell you that much about EteRNA, but I think it kind of just leads into it. So the great thing about EteRNA, unlike any other game that exists, is players are able to generate designs, and then these designs are actually tested in the lab. And what's great about this is there is a full feedback cycle, unlike other games, where people like myself and everyone else can learn from their own designs and improve them in the future, and we can thus learn things about RNA. So it's not just like a one way, it's not like we're just sitting on our computers predicting something. We can actually figure out whether this stuff will work. So this is, I think, as Rishu said in the past, this is like the
the true crowdsourcing of the scientific method. People can come up with their own theories, test them, and then get feedback on them. And really, I think this was covered by that nice video we saw about Adrian. But you can see this effect just based on the progress of EteRN over time. So this is back before the cloud labs, where we were just doing very simple designs, and we had the cutting-edge algorithms, NUPAC and RNA inverse for predicting secondary structure for these designs. And initially, when we started out, the EteRN community was doing maybe slightly worse on these simple ones. But then over time, even as these became much more complicated puzzles, the EteRN community eventually just kind of destroyed NUPAC and RNA inverse. And I think this really is like the thing we want to harvest, right? Like this is the fruit of everyone's labor here, is that these researchers have created NUPAC and RNA inverse, and now just people might just say some random people now can beat them, whom you would think would know nothing about RNA, but you guys now know a ton about it, and we want to know why. We want to understand this. So back a couple years ago, I'm sorry, it's a little blurry, we opened the strategy market to try to harness these strategies, like how are you actually doing this? And so using, we asked for your suggestions, and we ended up getting a couple of different algorithms. And here's an example from Eli Fisker, which now I think is one of the best rules about the directionality of GC-based pairs on multi-loops and two-way junctions, that these rules, or these empirical rules, are something we might have never discovered, but now we have access to because of this Cloud Lab system. So now, using these rules that we collected, that we now calling EteRNaBot together, you can see they now they can do slightly worse than human players, but definitely significantly better than other algorithms. So this is like hard proof that what is being done here is leading to better understanding of RNA secondary structure folding. So we've over the past 6 months, Michelle in the DOS lab has actually ported this, used this code to also do it for switches, and although it takes much longer because there's multiple states, in these, and I think if this was 2 rounds ago, EteRNaBot actually scored the highest score for this switch. So they definitely can compete with humans. Nando was nice enough to also point out that his Vinny algorithm also is near the top for a different puzzle. So they're definitely competitive with human players, but of course they were invented by human players. So I just think it's quite amazing, like the knowledge we've been able to extract from you guys. But there's really another avenue that I don't think has really been investigated yet, and I just pitched this to Riju a while ago, and like there's so much just data sitting on the cloud now with the cloud labs, like thousands and thousands of constructs. And we know what the secondary structure is and what the sequence is, and like, can we just mine this data to figure out, are there just features that will tell us whether a design will work in the future? So I won't go into tons of depth on it, but I decided to use a random forest algorithm, a regression algorithm, which is a kind of decision tree based on features. So like in this case, if you're trying to decide whether you want to play or not play, well, it's like, well, is it sunny? Well, if it is sunny, then I'm going to add 2 to play, 3 to don't play, so on and so forth. And if you just collect a number of features, like in this case, every one I can think of, like %GU, number of repeats, if loops are capped, if they're not capped, so on and so forth. You just feed it all this, hand it all the data, and be like, just tell me, is there some arrangement of the data that will get me something meaningful, some meaningful decision tree? And what you can see doing this, if I won't go into all the details, but you have to give it fake data too, or it does not. One of the big problems with random forest trees, it overfits very easily. So I handed it a lot of things I estimated that would not fold at all, like things that have tons of non-canonical base pairs. And real data, you can see first it separates it incredibly nicely. And then this is the training data. And then on the test data, so this is stuff it's never seen before, it gives you very highly correlated data with the EteRNA score. So this is the actual EteRNA score, and this is the predicted EteRNA score. And just to point out, on some of my own designs that I've generated, if you compare the EteRNAbot predictions to the actual scores compared to this model's, this model that I generated predicts it far better than this than even EteRNAbot. So I wrote a little website to use it. I think it actually went down because we crashed our one of our servers, but I'll get it back up, where I wrote a way for you to not only get a score based on the sequence and structure, but also I wrote a little interface where you can write your own rule and get it scored. Like, how well does it correlate with the existing data? And so just briefly, this was the last I checked. These are just some of the rules and how well they're correlated with all the data. So I thought it'd be an interesting experiment. Not many of you guys actually used it, so I kind of lost interest in it. But I thought I'd bring it back up, and yeah, that's it. I guess I'm more interested in what you guys think about bots and how you'd like to use them. Like, there's lots of talking of using them to help players during like solving the puzzle. And are you guys interested in that? And also, if we could, what do you think they should help people with? Should they help solve part of the puzzle? Do you want to see a full solution and work off that? So on and so forth. And that's what I got. Adrian, do you have a question, or you're just stretching your arm? Okay.
No, I have a question. Well, it's not so much a question as it's.
Do you want
like,
the microphone?
Oh yeah.
You gotta turn around. Switch it.
Hello? Hello?
Techniques for this one works. Okay.
There's one that has no battery.
Okay. Well, it's actually just, first of all, it's really cool that your bot is so well correlated. So I think it's definitely something that the EteRNA community should be thinking a lot about, is how to transfer our knowledge to computers. And I guess just a historical note about the results that you just said, because I think it's kind of just interesting and fun, is that I've mentioned this question of how would you learn what EteRNA players are doing to a lot of machine learning specialists. So you say to them, okay, so we have all these players, and they're playing this game, and you show them the game, and then they do this thing, and at the end of the day, the things that they're creating are better than the computers. And how could we possibly understand what's going on? And most of them come up with these really, really elaborate ideas of like, well, we'll model what they're trying to do, and then we'll build a thing and it's going to flip. And they think about it like, how can we write a computer program that literally plays the game the way the humans play the game? And it was really Riju's idea. I think it's sort of unprecedented. It's like one of the jewels of EteRNA, not well, I think, understood outside of EteRNA, which was just to say, like, let's ask the players, which was the base of the strategy market. Just ask them in plain English what they're doing. And then we got some grad students to code up what the players had said. And then we regressed on that. And that was, I think, such an interesting and beautiful idea. And I feel like
Anyway, I just would mention that historically, and also I feel like that's a good basis for how we can think about extracting knowledge from human minds and making labs in the future.
Maybe the panel can discuss.
Oh, should we do the questions first?
Oh, who's?
Yeah.
Okay.
Pass the microphone. Yeah. Oh, really?
So a couple thoughts. The first is that we should be looking at, if not fully iterative, at least multi-stage kind of formulations. Because I think one of the traps is to kind of look at the data and say, there is this magic that we will suddenly pump out of it. I find this at work as well, where we deal with big data sets. You know, that there's this magic that you will find a correlation and you will find the answer, as opposed to you will get close in the first iteration, and then if your program allows appropriately for iteration or multiple steps, that you're going to hone in on the final answer and really improve your accuracy. So that's certainly one area I'd like to see us go for, as opposed to just a flat, oh, where are the correlations and so on, and oh, gee, it didn't work as well as we would want. The second is, going back to the thing I was talking about people experiencing different parts of Eterna. I think very few folks have actually played around with the bots or the scripts or the strategy market. And I think we need to take some action to involve that into the lab directly. I think we need to literally have some labs that say, try these things and so on. It's a lab project, and it's a little different. It's based on the strategy market, or it's based on feeding ideas or so on. And trying to mainstream this into the things that we have people normally looking for and feel rewarded for, as opposed to, oh, it's this thing out there that's kind of, I'm not sure what it is, and it's hard. So.
Yeah, I totally agree. I think we have talked, developers have talked about trying to get better integration, but yeah, I guess where explicitly you'd want it. I mean, you think in the lab that's a place, or like have a separate type of puzzle where you can have bot assistance? Like, what? How do you see it?
Answer? Go on.
Oh. Is it done?
I did it to myself.
Okay.
Eterna has already got a lot of pieces, so the more you can mainstream it back into, it doesn't matter if it's a different kind of lab. Yeah, maybe it matters. It doesn't matter. Yeah. It doesn't matter if it's a different kind of lab, as long as it's just, you know, something where people are trained to look for it under the title called lab. For me, that's. So it can be quite different than what we currently think of as a cloud lab. That's all right.
Other questions?
James Lee. Yeah, I love the bots and wish I had more time to play with it. But one thing that comes to me is there's a couple of ways of doing things, and Poppy's talked about it, and that is that, you know, there's one thing where you've got all the data and you're trying to mine it for results, and there's some folks who are really great at that. Eli does it well, Ferb does it well, but there's also the point where you're trying to, you know, then play with an idea and think, how can I test this out? And there's something in the labs called the pilot projects, which I don't see being worked or being done, and I don't know if they're not running or if they're being run quietly in the background. But if it was easier for somebody to create a pilot project, I think, so they've got this idea, I think, you know, this might work this way, and maybe they, you know, there's some hints in the data or whatnot, but then if they could create a mini lab where they define the shape, they define 40 sequences, you know, they have full control over it. It gets run, and the results come back for everybody to see. You know, but you also encourage, here's the hypothesis, here's what I'm trying to test. And then you can have these like little mini experiments that are being run in parallel with the whole lab. And, you know, you can fit 100 of those for 400 sequences. And then you get a lot more maybe involvement of people trying to test out ideas and think of what might work and what not. Because once again, that's the part that humans can do that the programs can't yet, is to try and think up the crazy ideas of what might work and develop a simple way of testing it. And then the program in the lab helps us to test those ideas and see, does this work or does it not? With the bots, same sort of thing. You know, I love that we're starting to do the strategy market for switches because, you know, I'd love to write a bot that did switches, but I don't know what to put into it. I don't know what's going to work and what's not. I'm currently playing with something that tries to do a cleaned up bot, and I'm, spinning a few hundred of my 700 trials in this episode, doing variations on that. But I don't know what's required. I'm still trying to grasp at the switches. So if we've got things that can help players to check out ideas and try them out, and maybe shorten the cycle to figuring out, what to put into the strategy market, that I think the strategy might work, and then you guys run the numbers and crunch it and say, yeah, the data backs you up, or, no, you get like 0.01 correlation, it's not really worth it, But there's so much data, it would be helpful if there was some way to help us to, figure out what are the gems and what are not.
Yeah, I mean, that's exactly why we have the strategy market. But so you just want better integration, pretty much, between the ideas people are hypothesizing and then testing after, or sorry.
A little more structure in how we can test an idea, because right now I can do 20 variations on some design, but when it comes back, it's a large struggle to try and find those 20 results and pull them back together and see what, but if it's encapsulated together, and this was a little pilot lab that I ran, then I've got those results together, and maybe I can, thumb back and forth between them quickly and say, oh yeah, it worked, or no, it didn't, that was a crazy idea.
Yeah. What do you think about, I've thought about this, sorry to stick on this, what do you think about this grouping solutions? Like if it was in a cloud lab, and you're just like, these 20 are to test this idea in one puzzle. I think that's like a good.
That's exactly what I'm
Okay.
And
Good.
I mean, you could maybe do a similar thing with tagging. Where you say, I want to tag these entries as being, trying this hypothesis. But it would also help if you could do that in a separate lab that you define the shape.
Yeah.
And of course, if that particular lab was based on FMN and a microRNA, it would be helpful if your mini lab was trying the same thing.
Tagging is superior.
Yeah.
You shouldn't be trending towards grouping because it's one-dimensional. Tagging is going to be multi-dimensional, and it's going to be player controlled, and therefore it's going to be much more valuable in terms of both you setting things out prospectively to say, I want to cluster these things together that I've already tagged, and having other people say, oh, I found something interesting in what they did.
Where's the mic? Someone has the mic? Okay, sorry.
Hi. I wish that you would not give up on this because I think it's a way to validate the research and the data, and that would kind of bridge the gap. Putting our strategies in human words and then getting the data back from the lab, then how do we actually validate that what we're seeing from the lab matches these human phrased strategies?
Yeah.
And I feel like what you're doing does that. So I hope that don't give up on it because and I also hope that you understand that we all have jobs and families and things like that, and for us, like the timeline in which we participate with EteRNA is all a donation and volunteer work. So if you don't get a response quickly from us, it's not necessarily because we don't like your idea. It might just be that we're busy too.
Yeah. No.
Yeah,
I know. I'm such a slagger, but I mean, just to reiterate, we're not giving up on your idea of like taking people's suggestions, like we're doing the switch thing, but you're specifically talking about the EteRNA drone. Okay. Yeah, I'll try to get it back up. Again, we're having this server issue that we still have not fixed. So, yeah, thank you. That means a lot to me, actually.
I would say that I also agree with Jim and Robbie, just that I think that there's a barrier of entry doing the more complicated work, and it's just a matter of energy input versus reward. So if you leverage gamification principles to make sure that people feel adequately rewarded for their participation, then I think you might find higher levels of participation. And so one way to do that, I think that Nanda's work making the tutorial walkthrough tools will help with that. And chunking things into smaller pieces and steps will enable people to participate in more complex things that seem very difficult from an amateur perspective.
Yeah. I really like that idea. Yeah.
I'm hopefully going to kind of piggyback on a couple of things I heard, and I'm sure that in the panel that I'll be in tomorrow, we'll kind of touch on this a little bit.
Yeah.
But I think that one of the big things that we're looking at is that saying like I think creating bots that's really cool, but at this point I say, okay, great, I want to create a bot. So where am I seeing this information? I can't just go to a page, I can't just go to the scripting page and say, get started with bots.
Yeah.
I think that would be something really cool where I can say, I immediately have somewhere where I can just start and immediately see what I need to do to be able to make my own bot. You know, and I think that's true with a lot of different aspects of EteRNA, is that there's a lot of different things you can do, but it's just you're dropped in, you have the basic tutorials that's going to, of course, improve. But then you say, okay, go have fun. Obviously, the first place you go is the challenge puzzles, and you're kind of just lost from there. There's a lot of great things that I'm sure, like, I would be interested in, but I have no idea where to start. And I think that's one of the really, really big issues there.
Yeah. Well, we're totally aware of that.
But
yeah.
I have no idea where I would even begin.
Yeah. Well, we're totally aware of that issue, and we are actively working on that. So yes, I totally agree with you. That should have been solved a long time ago, but it's what it is. Anything else? Should we go through the panel?
Yeah.
Yeah.
So I don't know like what panel's ideas and bots are. Michelle. So.
Hey, I just wanted to start talking a little bit about bots. We do have a couple of ideas. In the puzzle itself, there is an interface for allowing scripting to work. And we do have a couple on the dev site that is able to pull the script in and be able to run the script. And as everybody here knows, the players, there are scripts that work as bots that do solve the puzzles. So basically, we can tag any script we want to a puzzle and have it run. That's available like on the dev site, but we haven't really understood how we want to integrate that into the game right now. So I mean, it's hard saying, okay, I want a list of all like 500 of the different algorithms that we have now and pick one and let's have it work. So that's one of the problems that we have, like just to understand how we want to tag a script to the puzzle itself to be solved. Another thing that we've been looking at is to actually have a way for the players to build their own type of solving system. Instead of like, okay, we have to go to the scripting interface, which only a few people like Jay Anderson Lee has done, Nando has done, to be able to use their scripts. We would like to have something a little bit simpler so that the player can go in and say, okay, for step 1, I want to do this. For step 2, I'd like to do this. I know EteRNAcon has been using something we call like a brute force spot, which basically takes a long time for it to run. We'd like to use something along those lines, but have a trimmed down set of rules. Like, don't go through every combination. Try this combination first. If it doesn't work, then try this combination. Maybe go through the motives. Like, let's say we start off with the tetra loop and then the certain internal loops, and then when we got that stabilized, then you could work on the stems, the stacks themselves. So we are looking at these ways of being implemented. Another thing that came up was for these labs where we do have a lot of player submissions that we'd like to get. It's hard for the player to keep going through and saying, okay, let me take this design and do a mutation or two and then submit it again and do another mutation or two. We would like this bot to be useful in the lab so that you can set it up and say, give me the first or the top 10, the top 50 different submissions. Run through it, give me a list of these selections. If I like them, click a button, submit all 50. And basically it would be tagged to the player itself. So we are looking at these type of tools to be able to implement. And I think Joe is alluding to it, but those are some of the details that we were talking about. And we do have different methods of trying to implement it. For some of the people that are active on the dev site, they can see a little bit more into these tools also. I know.
Michelle implemented one of those.
Yeah.
So we can comment.
Yeah, well, basically, one of the things that we did do was on the dev site, we have a special constraint that you have to get a similar score to what EteRNAcon has scored. So if you get, let's say, a score of 95, which EteRNAbot would have scored, that's basically solving the constraint, and it would allow you, or it would give you a good indication, like, okay, we're satisfied with the solution. You can submit it. Basically, Michelle worked on this, and that's something that she had a big hand in.
Yeah, I'm gonna
That
ask
was
her.
all Nando, that was Tommy.
Well, it was both of you working together, so.
Well, I want to see if Nando wants to jump in. Nando,
Give him the mic.
Nando, do you want to unmute yourself and want to say a few words?
It's 2 o'clock in the morning here, so sorry guys. Can you hear me?
No, he's changing his thing. He's just,
He died.
He died.
Oh, no, he.
Can you hear me, guys?
There.
Yeah.
Hello?
Yeah.
Yeah, so.
Oh, he's demoing the.
He's demoing something, but we can't hear him, so that's a problem. No, can't hear you.
We can't, no.
Okay, there you go, there you go.
Now you hear me?
Yes, yes.
Oh, fantastic. So, yes, I disagree with Michelle. She did the hard work here, not me. And yes, this new constraint here is simply an implementation of the EteRNAbot as a scorer, and it simply judges your design. And so here I'm going to rake it up, for instance, with a simple flip of a base pair. I could also probably demonstrate how bad a Cub Scout looks like, and we still have here the structure that is solved, but the score is of course much lower, and I find it a very interesting application of the scripted constraints I've been trying to implement. And Michelle did a great work in porting the EteRNAbot to JavaScript, which allowed me to make this. I feel that this would be probably in the future a very nice introduction to lab work for new players, because they could try to get a sense of what kind of combinations, what kind of sequences and work for certain structures. So that's very interesting. By the way, Joe, if you allow me, I would like to ask you, your random forest tree algorithm, do you think you could port that to JavaScript?
Yes.
Because then I could eventually make it into a constraint too, or.
Yeah, we can definitely talk about that later for sure.
All right.
Very simple. It's very, very simple.
All right, that would be awesome, definitely.
All right.
So, yeah.
The what?
The script bar Nando made.
The
automatic solve.
Oh yeah.
Oh, should we demo that?
Yeah. Nando, can you demo us the automated bots that you and Michelle did?
Yeah, just a second. I think I'm on the right Just give me a second, guys.
Yeah, this is what I was talking
So
about.
that's the magic
here,
code.
Where you put the script ID in, and it's able
Yeah. So here there is a little bar that is currently a hidden feature, I would say. So what I'm going to do here is to reset the puzzle to nothing, and I will switch it to the native mode because it's the more fun way to see it happening. And here I have the script started, and I'm giving it 1500 iterations. And as you can see, it starts mutating during the calculations, and boom. In this case, the script is being very lucky. I tested it in some other puzzles, and it never finds a solution, because this is also a very, very crude solver. This is pretty random. Maybe Michelle could say a few words about this implementation, but I don't think she made anything very, very smart in this one. But in this case here, it works pretty well.
Yeah. So this is kind of where we're headed. I mean, obviously, I understand it needs to be clearer than to some random number. But
yeah.
Do you guys want to say hello?
What it's doing is basically like, hello. Okay. What this is doing is basically making random mutations and seeing if it's getting better. So it's much less complex than the thoughts that I'm sure you guys are writing. But we're hoping to make some to this, including like figuring out how best to sample different sequences. So instead of just like making random mutations, we can maybe use some of your suggestions to say, oh, usually I put a GC pair at the end of here first, and that could maybe like improve this and speed things up also.
You do know there is a sequence of lab puzzle solvers called random mutations, which Eli and Matt and I worked on, and it does do exactly that. It's got modules in it that you can, if you're a coder at this point, but you can, code a strategy and say, oh, I want to do this in this particular kind of circumstance, and then play out different modules against each other, and then run it on the puzzle, and it'll do 10, 20, 100 iterations and hopefully give you a solution. So that's the same sort of thing where, if we can make it easier for players to do those modular things, say, I've got this idea for how to work with this kind of situation, let's try it out. You can either try that in the strategy market approach, which is to say, let's run it against the labs and check it, or let's run it against the puzzles in a bot type situation and see what it solves.
Yeah, what we were doing here is just a proof of concept to see how we can implement it and how we can get it to work. So yeah, there's further development that we want to use it for.
Any more questions, comments? Vineet, you were kind of silent all the time.
You did just get invited to the show like 20 minutes ago.
Yeah, I'm sure. Long day.
Okay. So this will formally end. This will end the formal portion of the talks. We have dinner. Dinner will be catered here at 6 p.m. outside the building. Same place. It's gonna be West Coast deep dish pizza.
Oh,
so
that's random.
hope you guys like it. There's also a vegan option, so those of you that are vegan. So yeah, hope to see you there. You can walk around campus. It's very pretty. Oh, by the way, before you leave, that's true. Thank you. So we have some T-shirts from previous Eterna gatherings, and we would like to give players the players T-shirts. We have 18 T-shirts, and we know that we have like around 15 players. So if you're a player, come to me and I will give you a T-shirt. Right now. Thank you.
The sizes might not match.
What?
The sizes might not match.
Yeah, sizes might not match, but